Okay, so fine. Today's agenda would be basically HelloPa, but as a precursor, you need to leverage several things from the HAZOP. So, and since the HAZOP course was, or the HAZOP training was given by Yashpal sir, maybe more than 6 months back, so I would also like to touch base with the HAZOP fundamentals, and then we will look at the LOPA screening, and then we look at LOPA, layers of protection analysis, and then SIL assessment. How do you use LOPA for SIL assessment? Okay. Yeah. So what you will learn in this course, of course, fundamentals of hazard identification and risk assessment, or HAZOP studies. Many of them refer to them as PHA studies versus hazard analysis. Then basics of bow tie diagrams. So this is an add-on or an icing to the cake because bow ties are very seldom discussed about, or you get very rarely you get opportunities to explore bow ties. So I just wanted the forum to be, exposed to maximum fundamentals of process safety. So this bow tie, and at some point it does find relevance in our course. So I had to bring this up. Next is LOPA screening. Obviously, not all scenarios are applicable for LOPA. So we will discuss that in the successive slides. So for applicability and exclusions, there are several scenarios which are exclusions like human errors which could be conducted. So those we'll discuss later. Next is fundamentals of LOPA methodology along with three types of actual industrial scenarios. So there was an emphasis to have the real life, industrial scenarios. So basically, we just did in fact, same team with Shalini and others on the same team. We did a LOPA just a couple of months back for Stanlow refinery. So we've taken that as a basis for your better understanding. So we have three examples from that industrial exposure. So next is emergency. Yeah, Shalini, this again you would like to go through emergency preparedness. Shalini, would you like to take over for the emergency preparedness or?
No, sir. If you want, you can continue. No issue.
Yeah, so basically this is just emergency. I'm not sure whether you guys are all in the comfort zone of your homes or in the offices or conference rooms, but just be aware of the basic emergency preparedness. Like you have the information, projectors and information displays. Next is what is the siren types, evacuation routes. Obviously, evacuation routes are very significant for safe exit and evacuation. Next is assembly points. Assembly points is important because they need to ascertain what number of people have actually been evacuated from the building, and then the residual people who are there in the building, they will have to have a plan. So that is where these assembly points come into play. Next is HAZOP. Yeah. So just to break ice with you folks and to make it slightly interactive and see how far you guys are, actively participating, we would like to have this interactive question. So the question is, what percentage of data from the HERA or HAZOP do you think can be leveraged for LOPA and SIL assessment? So these are the three answer options. And Shalini, if you can bring up the voting, this. No, don't put it in chat. Hold on. I think Shalini, you'll bring up the voting with this, right?
Yes, sir. Yes, sir. I'm just.
Yeah. So yeah, folks, just wait. Let Shalini bring up the voting, and there you can vote. So your answers will
be in the chat box. They can see.
Can I see that also?
Yeah, it is there, sir. Poll. They can answer the.
Okay. Is that, or we still have responses? When do we stop? There are 49 responses only. Out of 198 attendees, only 50 have responded. See, just again, reminder for the attendees, there is a chat box where Shalini has posted the question and you guys have the liberty to vote there. So submit your vote and then so we would have a fair idea of what is the pulse of this forum. There are 198 members in this session. Why only 52 responses? Come on. I want you guys to be awake for this because there is a lot of learning through the day, and I really want you guys to be awake and involved in the session. So that is why just at the start of this session we have this polling. Because the rest of the part could be, I will be running through these slides, and I don't want you guys to miss on the technical aspects or the important focal points. So please, can you guys just respond to this question or voting? It's in your chat box. We have 208 people, 208 participants or on call in this forum. How many are there in YouTube, Shalini?
YouTube, let me check.
And how do you post this on the YouTube also? How will they respond?
They can respond in the chat box because they are seeing our slide now. The question is there, so they can just put their.
For YouTube guys only, in the chat box.
Yeah.
Okay.
Yeah.
I will not start the session unless I had 206 responses or votes. That gives me a lot of liberty. Come on, guys, please vote. Shali, you're doing the timekeeping. How many more minutes you want to let them to vote? 2 more minutes.
Okay, sir. We can wait for 2 more minutes.
It's 10:28.
Yeah.
We close up at 10:30 for the vote.
Yes.
Last 1 minute. We have only 61 responses. Last 1 minute.
Sir, it's 10:30, so now
Yeah,
I'm
okay.
closing the poll. Okay.
So we have 62 responses, and just because I want to give you guys the privilege of voting through the session, so I will declare the results at the end of the session. So that there is suspense as well as you guys are hooked up to the session. Yeah. So Shalini, maybe at the end of the session you can convey a record of this along with the other votes. Yeah.
Okay.
We'll look back to the results then. Okay. So as we are aware that a good percentage of from your responses as well, you can see several have responded to 50 to 70 and 70 to 90%, which is the majority. So from this we can understand there is a good leverage that can be carried from HAZOP into a LOPA session. So that's the reason essentially we'll touch base upon the fundamentals of HAZOP and then move on to screening and LOPA. So Again, we'll disclose the results at the end of this session. So stop voting and stop, or keep voting and stop the chat chat part. Yeah, fine. So moving on to next slide. Why doesn't it go to the next slide? Because I've selected chat, is it? Okay. Okay. Yeah. So the next slide, again, see, as all the studies are dictated by certain standards, so HAZOP itself is dictated by IEC 61882. And then the definition, or this is a textbook definition, which says the HAZOP process is a qualitative technique based on the use of guide words, which question how the design, interiors, or operating conditions might not be achieved at each step in a design, the process, operation, or procedure or system. So this is a textbook definition. Obviously, many get lost trying to interpret that. So I will try to simplify this decision, what you call definition for you. Okay. Wow. Okay. So just simplifying this definition and trying to break out things for easy understanding, or you can say this is the way I define it. So HAZOP is a holistic study of a system or a node to evaluate all credible hazard scenarios that are collectively addressed by a multidisciplinary HAZOP team to ensure. So what do we ensure that is important? First is risk elimination. So these are the three intentions of doing a HAZOP, that is risk elimination, risk reduction, and risk mitigation. The risk elimination is basically achieved by doing an inherent safe design. Okay, like you take an tank with an overflow, route it to a safe drain. So that way you are ensuring that any overflow or spillover does not form any, slipovers or any combustible mixtures in the vicinity. So that is one safe way of doing an inherent safe design or eliminating a risk. Next is pipe. Discharge piping is designed usually for the pump deadhead conditions. So whereby if you guys have looked at the pump curves and the pump deadhead conditions, so basically many a times they design the piping or the pipe rating is more than the deadhead pressure. However, many a times this could be an overkill because there could be exorbitant cost of piping material involved. So that is the reason in those cases they don't preferably go for those deadhead conditions, and then they design the system, or they do the risk reduction by providing adequate controls or safeguards. Like you have your PPCS system, which is your basic process control system, or your ESD emergency shutdown loops, or your SIL rated systems and SS systems. So these are where you do a risk reduction basically. And then once both this risk elimination, reduction is achieved or is not been achievable to an extent to the satisfaction of the project or management, then we look at risk mitigation. These are basically providing recovery barriers. So basically this comes into picture when a risk or incident has already occurred. And in that case, you look at measures to contain the event or the catastrophic failure. So in that case, you have examples like your tank bund or a tank dike, whereby it contains the total volume of the tank. Essentially, they are designed for 120, 125% of the volume. So they are well equipped to contain the inventory from the tank in case of catastrophic failure of a tank. And obviously, as I said, this is a recuperative measure or a mitigative measure. So that is why it is listed as a recovery barrier. Next, you have fire and gas detection systems. Obviously, your FNG systems come into play after there is an incident or a leak. Obviously, they do contain sometimes they isolate the inlet flows, so that gives us adequate liberty to say that they are considered good recovery barriers. But then there is still a considerable amount of inventory into your tanks or piping that can also cause this. So that is why it is referred to as a recovery barrier and not a prevention barrier. Next. So this is what is the definition. Basically, it is a holistic study of a system to ensure risk reduction, risk elimination, and risk mitigation. Okay, next is different PHA tools. Now we have hazard and INVID, which is hazard identification or environmental identification. At what phase or what stage of a project these are done? So this is very important to understand. So hazard and INVID usually done when there is less data available. That could be at a feasibility or a concept phase where you just know that what compounds or what chemicals you're using and what could be the terrain and other things for the INVID. So that or the environmental conditions for at that site location. So based on that, we just do it at the initial stage when there's lesser data available. Next is an HAZOP, which is done at the basis of design stage, or you call as the BOD or the field stage, or at the detailed phase of a greenfield or a brownfield project. So that is when you do a HAZOP. Next is what if. Say again in HAZOP there are two instances where you do it. It is an early phase of the project during the detailed design when you have 30% of design available, or at a 90% stage where it is called the end of detailed design. Then you have what if. Now what if is done for smaller brownfield modifications where you are not looking at all the guide words, but you are objectively targeting only the changes in design. So that way you confine yourself only to the, like, whenever there are management of change MOCs or any small design changes, they look objectively at what that changes are having on your holistic design. So that is when you do a what if. Next is LOPA, as we are going to address today, is layers of protection analysis. Then this is done typically post a HERA or a PHA review. That means, as we say the earlier voting, where we realize that a good percentage of data from the HERA or HAZOP is leveraged into a LOPA. So that is why we do it after the HAZOP study. And it is holistic safety assurance and SIL determination. Basically, this is done for safety reassurance that we are within our ALAP range, and for SIL determination. Next is BOTA analysis. Now, this is done to determine the risk mitigation recovery barriers. Basically, if in spite of all the safeguards, there is still a possibility of risk occurrence, and we look at risk mitigations, as we said in the earlier, risk mitigation recovery barriers, which we can also take credit of because they prevent the further cascading of that incident or further catastrophe of the incident. So in that case, we take the credit of these recovery barriers, which are discussed in a BOTA analysis. Okay, next, HAZOP is done at what phase of a project? Again, we said HAZOP is done to a certain plant safety and can be done at different phases of a project. This is very important to understand, because not many of us would have essentially worked at different stages of a project or a full life cycle of a project. So we are usually typically in the design or in the engineering phase, but the HAZOP can be done at different stages. One is the design and engineering phase, where you do it at 30%, as I told you, preliminary HAZOP, and at 90% where you call it as a detailed HAZOP. Now again, some clients, basically globally in Middle East and Europe, they do a design review, which of late many of our Indian clients have started to do. So that design review can be done before the 30% preliminary HAZOP, and followed by the preliminary HAZOP and detailed HAZOP. Next is post-construction prior to startup. So this is where, just before startup, they call it PSSRA, HAZOP at pre-startup review audit, PSSRA. So this is many a times the clients insist on doing this at site, with the site, essentially because it is a site analysis. We have the full site team, engineering as well as construction and the operation teams. So who converge to ensure that just before construction, we have all the things addressed, all safeguards have been taken care of, and there are no more gaps in the design. Next is during operation. Now, this is a very important aspect which not many of us would have realized. There is something called as revalidation or re-HAZOPs, which are done every 5 to 10 years for plant integrity, to check plant integrity, or to look at insurance premium reduction. Or see, again, plant integrity means with regards to in the 5 or 10 years, you would have done several modifications of a plant. You guys must be maintaining a master PNID and master documents. So you tend to update those masters for whatever smaller changes, and then you take those master PNIDs and you use them either as a basis for your revalidation HAZOP, or you look at an as-built PNID, so that whatever changes that have undergone in the past 5-10 years would be taken care in an as-built PNID set, and those would be considered as basis for HAZOP. Next, you do it for insurance premium, because insurance in oil and gas, or any sector for that matter, is considerably high. So that insurance amount reduction or the premium reduction can only be achieved if you have done an HAZOP at a timely level, every 5 years or every 10 years as required by the insurance agency. So that is important again. Or they do it at a stake sale, because the new buyer or the new purchaser of your asset would essentially not know where the gaps in your design or safety are. So they would emphasize on doing such a safety or integrity check before they go for a stake sale or stake purchase. So that is another instance where you do a detailed HAZOP or a revalidation HAZOP. So next we look at, as we said, there are all standards for different studies. So we have standards for HAZOP, which is basically IEC, International Electrotechnical Commission, and they have this risk management assessment techniques, IEC 31010. Next is IEC 682, which is important here. That is exclusively speaking about hazard and operative studies. And then IEC 615 is a functional safety document, which essentially has good part of it reference to the HAZOP and the safeguards we consider. and this is safety instrumented. And there is other one for loop also we will be discussing later. Next is these are the typical softwares we use in the industry. It is as per the insistence or request of the client. One is PHA Pro version 8. I think there's a new version now. This is by Sphera. And then PHA Works is by Primatech. Essentially, it is the older version of the, maybe 10, 15 years back we used PHA Works. There are several clients who use PHA Works even today. And then the most simplest one is our Microsoft Excel template, which is the list of standard deviations as per the client requirements. Obviously, the standard deviations could be different for different set of industries. Like I've worked for oil and gas, fertilizers, pharmaceutical, pulp and paper, metals, power sectors, renewables. So everywhere they have a different set of guidelines. You have these set of guidelines are more or less defined in IC 6182, but they are tailored based on the requirements of the client or the industry or the sector which we are catering to. Next is, okay, so at this point, it is imperative to bring up this, layers. Although we are in the HAZOP phase, I want to bring up this layer of protection diagram, because this is how we look or we address a system, whether it is inherent safety design, or HAZOP or LOPA. We look at a system with a holistic view. If you look at this PFD, I think my pointer is visible, right? So this, if you see a tank and you have those hoppers and other things there, so that is where your basic process is working around. You have a process parameters and guidelines set around that operating envelope. So this is what you call an operating envelope, the first layer, where you have defined your process parameters, temperature, pressure, flow, and other, composition and other things. So that is where you provide a set point, and this is your operating envelope. So we expect the process to run within this operating envelope, but that is not that is an ideal expectation, but that is not how things happen in a real life scenario or during practical operations. So during practical operations, there is always this possibility of the parameters going beyond this operating envelope. Okay, so that is where your basic process control. You see, there is a process one, and then there is this is slight process deviations which you consider in your over design. The first process is that over design. You guys consider 10, 15, 20% as over design. So until that point, obviously your process is still well equipped to take care of any deviations. So beyond that is what you set your process controls for. Now these process controls are different, pressure transmitters, and then you have your control valves and different controllability aspects within your equipment also, which tend to bring in your level control, temperature control, pressure control, which tend to bring back those parameters back to the level of this operating envelope. Okay, so that is your basic process control system, which is essentially your first layer of protection. As we designated, the old design part within that should not be considered. It is part of your system. Then after the PPCS is what you have your alarms and operator intervention. Now this is again a very important layer. Some people will take credit of it, whereas many clients do not take credit if there is no adequate time for the operator to respond. Like just last year, we were in Spain, where there was an offshore, offshore platform where they were having this windmills and other things where they were generating considerable power in Europe. But however, that platform was manned with only 52 days in a year. So they had rest of the days, obviously the operator was working from the shore and they were required to go to the platform. So in that case, that client was insistent in saying that we will not take any credit of this third layer, which is alarm and operator intervention, because they don't have a full-time operator there. Plus, whenever there is a requirement, that operator would need at least 45 to 50 minutes to reach to the platform. So essentially, many of them don't take credit of this layer. However, if there is adequate time, if there is operator on site in the vicinity and there is adequate time for the operator to respond before the process safety time, we will look at those definitions. So before there is any incident, if there is a time for operator to respond, we do take credit of it. So next layer is, now if the operator is not able to respond, obviously you need a backup system, which is an automated system to ensure that your parameters are still contained within the set values, or they are brought back to the set values so that there is no event. And that is achieved through our SIF systems, or safety instrumented systems, which is your essentially you have your pressure transmitters go through a logic solver, through a DCS or a PLC, and then that is controlling a final element, which could be your pump, or you could be an ESD or whatever. So those are typically assist systems. The whole loop comprising of the sensing element, the logic solver, And the final element is part of your sys systems, and we will look at this more detail during the LOPA in-depth review. Now, these sys systems are definitely called as penultimate safeguards because they ensure that you are we are able to achieve something with an automated measures and without any release to the atmosphere. However, if these systems also fail, then you have your ultimate safeguards, which comprises of physical protections like your PSVs, your relief discs, or your rupture disc, or your vacuum relief PVRVs, pressure vacuum relief walls. So these are other layer which are referred as ultimate safeguards because these are mechanical safeguards and they are not vulnerable to the failures in your sensing element or your logic solvers or any soft link or anything. They are typically driven by the process parameters and they are mechanical devices, so they are bound to open. So their reliability is considered more robust than these penultimate safeguards. So that is why they are called physical protections and they are more reliable. So after this layer, you have another layer which is called as physical containment and burn. So this is basically what we said as the recovery barriers or the mitigative barriers. So here what you have is basically these bunds or the dikes around your tanks. They tend to contain the failure flow or the inventory if there's a rupture of a tank or catastrophic failure of any of the piping and other things. So that is where you consider this as another layer, which is basically a physical bund. Obviously, it is referred in layer of protection, but not many clients tend to consider this as this. It is still a containment and prevents any further catastrophe because it prevents further aggravation of the incident. So that is why it is also they have listed as a protection. Next, after this is a containment, physical containment. Then you have fire and gas systems. Now your fire and gas systems are in and around the vicinity of the equipment or the tank, basically where you're protecting. And essentially, what they do is they either alarm the public who is working in the vicinity or the operators working in the vicinity, or it could be the general public who stays in the community beside the plant. So these are fire and gas detection systems are a kind of alarm layer. They are considered as a layer of protection because they are isolating the inventory. Many clients tend to isolate, or it is a important practice to isolate the inlet and outlet to that equipment if there is any incident or based on their fire and gas detection. We have seen instances when not many clients want to do it because it requires considerable automation, plus you need higher rated ESDs for those, so they are reluctant to it. But that is how your general philosophy should be. If there is an incident, you need to isolate any fuel, or you call it avoid fueling the fire in scenario. Okay, so you isolate that fuel to that incident, and that prevents the fire from further, catastrophe. So that is why this is also considered as an additional layer of protection. Now, even if this layer of protection has been lost, or even if we are gone beyond this layer of protection, then you have plant and emergency response. Now, this is very important. Many times we have these. You all guys are aware of Bhopal gas tragedy, So there you see that there is this. Just give an example, not to point fingers to anything, but that is where your plant emergency response comes into play. That if there is a gas detection of some very high kind of H2S or chlorine gas or anything of phosgene that was in that instance. So in that case, basically that specific. Now remember, you need to have that specific gas detector there. Okay, you cannot have a generic gas detector and claim that will take credit. You need to have a specific gas detector which will alarm the community to evacuate, or which basically will ensure that your emergency response comes into play and they evacuate the community. So there are several instances that the community could be on a small island and then it would become difficult to evacuate. So all those emergency response is part of that safety planning, whereby the whole community can be evacuated. And this is very important in across the globe because your land planning or your industrial planning is based on this emergency response, and that is how you get your licenses or your approved from your regulatory or a statutory body, where you justify this through QRS and other things, that these we have adequate plant emergency response in case of the worst. If all these layers have failed, and there is an emergency response that needs to be activated. So that is the plant emergency response, which is essentially to alert the operator to move away from the plant. And as I said, the last one is the community response, which is basically looking at general public who have not subscribed to this emergency, or not subscribed to this risk. However, they could be part of the operator family who is staying around the plant, or they could be general public. And that is why it is important to have, like, just 6 months back, I was in what to call this Kakinada, Andhra Pradesh, and just 200 kilometers from there in Vizag, there was this there was a potato chips making factory, and then I was surprised that they had to evacuate 280 families because there was ammonia leak. And then I realized, then it was in the news that they used ammonia chillers there, and basically these chillers, due to whatever integrity issues or they were not run for a long time, there was an ammonia leak in them, and that is when the detection was witnessed. So they had to move 280 families away, from that vicinity. So that is where these important things come into picture. That is why you have your fire routes map, your escape route analysis, all those things. At this point, you would have realized why we are doing it as part of the study, but that is the imperative part where you realize that how you are going to evacuate such higher loads of plant operators as well as the community from the incident location. Yeah. So I think this you guys can take a screenshot, or you can have this for your records, or I think it should always be there in the presentation, right? Shalini, it will be in the YouTube as well. So you guys can have this as a future reference. So this is very important. Next. Yeah, so next is the HAZOP team composition. Obviously, for the success of a good HAZOP, you need a right composition of a team, because many a times you have seen that when there are vendors involved, they send 2-3 people to the HAZOP forum, but it is mostly the sales team which are absolutely lost when you ask them many technical questions. So it's imperative to have the right composition of the team. So the mandatory attendees are the HAZOP chairman or the facilitator. Next is the HAZOP scribe. Then most important is clients operations representative, client site HSE personnel, then consultants. So like there are many EPCs involved, so it would be consultant process or the package lead. Next is vendor technical representation. Okay, so this is again important at 80% HAZOPs we don't proceed with. So all these mandatory attendees are required for an HAZOP to initiate or function. Without any of these mandatory attendees, the HAZOP chairman has the right to recall the whole session or just to call off the session. And there are instances where we are compelled to do that without an operations representative, because like for a vendor, the end client could be an EPC. For an EPC, the end client would be an operating company, an E&P operating company, exploration production company, or example, a manufacturing company. And for a manufacturing company, the end client is operations. So without the operations, we are not, or we are obligated to cut the session there itself without operation presence. And similarly, you need right technical personnel at the 80% HAZOP, because they are, if there are package items, they are well equipped to answer any concerns or apprehensions raised by the forum. Next, we have the support team, basically, which is part of they will be part of the forum, but they can be on call, or they can be, in and out, or could have staggered presence. So then we have this client PSM representative, we have consultants, instrumentation engineer, consultants, piping engineer, package specialist, and other deemed as essential. So basically, whoever SMEs or any essential, they can be non-continuous, but it is good to have them in full time. Yeah. Okay, next is important documents. Again, it is very important to have the right set of documents in HAZOP. I've gone into HAZOPs where the systems are so confidential that they would not even share the PNID. The PNIDs were brought up right in front of the forum where we were joined, and then they were like, we didn't have the privilege of studying the PNIDs or anything. They took us through the PNID because I don't know, they were skeptical about their patented, molecule or composition and those things, products. So we do have systems there, but my only we have dealt with it and we have addressed them successfully. But my only concern in such cases is that there is always this ambiguity left with regards to addressing all gaps in the of the process. So essentially, it is good to have, or it is required to have, at least for these non-licensor products or something. It is good to have these required set of documents. Like you have PIDs issued for the HAZOP post a formal review by client. Obviously, I've seen instances where they bring up the PNIDs and the client in the forum says that we have not reviewed this revision at all. In fact, the revision 0 also was brought into the HAZOP, and then they have named it as issued for HAZOP. And the best part was the client had not reviewed that. So that is a major drawback. And all those who are from EPC, please keep this in mind. The client needs to review at least one revision of those PNIDs, and they need to, if there is privilege to review or they should be also reviewing the issued for HAZOP session, but at least that should have been sent to the client. Tomorrow they should not come in a session saying that we have not received any issued for HAZOP session. Okay. Next is process safety information. Now there are some basic process safety information which is imperative for the successful HAZOP, and that should be available in either of these documents. Okay. Now, many of them have a very standard OCSP, which is called as Operating Control and Safeguarding Philosophy. So that document defines many things. However, not many clients have that privilege of having a very structured list of documents. So in that case, there at least you need a cause and effect or an interlock list or with alarms and trip settings, and then you have interlocks well defined on each PNID. This is again important. Just interlocks being part of the cause and effect, or this is not of benefit, because you need to have them on the PNID, not just for the HAZOP, but even during automation at site. The automation team is not part of the engineering all the while. So it is good that they have this information on the PNID. So whenever they are doing automation, they do it. Or like, to give an example, if you have a control valve which is fail open or fail close, and you have indicated that on the PNID, so that is how the automation will configure it. If you don't do it, or if you don't mention those things, so the interlocks or the safeguards or the PNID, then basically there's always going to be a gap. And then I've seen instances in Middle East where 40% of the control valves which were required to be fail open were configured as fail close. And that is a big thing. We realized that during the revalidation HAZOP, it was an 18-month revalidation HAZOP. And during that instance, when I raised this question and asked them to do an exercise, they came back within 1 week and realized that 40% of the control valves were wrongly configured. So these things can happen because you are either not mentioning them on the PNID, or your automation vendor is not part of your engineering, or they don't have the prerequisite documents to configure them rightly. So it is important to have that indicated on the PNID. Next, again, you have support documents, and what is important that the data should be consistent with the required documents and the support documents. There shouldn't be discrepancies, in which case then we are obligated to consider whatever is applicable. Like for an HAZOP, we would consider the data available on the PNID, but many times the equipment data would be contradicting, and that could be lead to further delays in the forum. So that should not happen. The data should be consistent in the support documents as well. The support documents are basically equipment data sheet or of comprising systems. Basically, all the equipment that are in part of the PNIDs or the nodes or systems, they should be available in equipment data sheet. Next is pump curves. Usually, you need these pump curves, which are very important. Many of the times you tend to miss it, and this is required at least at the 80% HAZOP or 90% HAZOP. We need this because half of your HAZOP scenarios would be discussed or addressed based on these pump curves. Next is piping material specifications. Many a times I have gone into HAZOPs where the client piping guy, they mention the things like, okay, this is our 300 rated system, 600 rated systems, but that may not be consistent with what the piping material specification says. So I always insist on having this PMS, because you have, based on the line specifications, you have these well defined in a PMS. And many a times the interpretation could be an error, not just based on the piping engineer, but from even all the engineering disciplines. So essentially, it is good to have this document whereby that becomes your binding guideline for any review. So essentially, piping material specification is a must. Next is material safety data sheets. Now, these MSDS for certain components, which are exclusive, like you have MSDS available easily on the internet, but many a times we have these proprietary compounds for licenses where they have their special set of MSDS for those set of compounds. So that should be available in many HAZOPs, because they dictate what would be the severity of an event or incident, and that is how we have to mention their criticality. So that is important. Next is additional reference as applicable, like basically hazardous area classification, fire and gas, cause and effect, oxygen depletion calculations. Now this is very important in pharma fields or biotechnology fields or API drugs, where you have oxygen depletion in certain confined spaces or in certain locations. And that is important because that oxygen is mostly replaced by nitrogen, and that nitrogen could lead to asphyxiation and other hazards for any operator who is going there, in that confined place or in that vicinity. So many times they have this buddy system also there, whereby there is one person starts hallucinating the other or asphyxiating the other, can come to his rescue. So again, these things are case specific, industry specific, but it is good to have them. And all of this should be part of an HAZOP info pack. The worst part is of late, many clients, they are so tight with the schedule that they just run into a HAZOP with one set of PNIDs, and they ask the project guys, they ask us to do that, which is not the right way to do it. We need to have a formal HAZOP info pack. And the reason I'm insisting on this is, and this is for all project guys, is because if there is any if there is any audit, the HAZOP info pack is your driver. You will be lost finding the data in other cases if they go for an audit. Secondly, for all regulatory and statutory approvals, these HAZOP info packs go along with the reports because they are the drivers, and that gives some kind of assurance or reassurance to the statutory body that this has been done in a systematic way. So always have this habit of all the project guys, EPC guys, or even your process leads insist on HAZOP info pack. It is a little cumbersome activity, but it has enormous benefit down the line. Next, node markups on PNID. Okay, now nodes on PNID can be marked based on several criteria. Most common ones are based on unit operations or independent systems. Next is based on pressure ratings, like specific spec breaks or pressure variations in the process. Again, you can base them upon temperature ratings or temperature variations in the process, or on different modes of operations, like normal operation mode, turn down mode, regeneration mode, flushing, cleaning, blowdown, hot blow, steaming modes as applicable. So these are different modes where you can provide your nodes based on these different parameters. Next is fundamentals for approach of an HAZOP. So first is always there should be a single discussion in a forum. Mutual discussions to be targeted towards the chairman, because that prevents people discussing on different tangents, and then there is inconclusive discussions. The discussions go in haywire mode, and there is absolutely chaos in the forum. So that should be avoided. Most importantly, causes need to be in the reviewing node. The consequences could be in other nodes. So this is very important basis we consider, especially for greenfield HAZOPs, where you have the cause should be in that node, and the consequences could be in any further nodes. However, there are exceptions to this basis or approach, whereby you have kind of brownfield studies, or you have debottlenecking studies, or revamping studies, or revalidation HAZOP. In that case, the cause could be in any node and the deviations could be any node for review. But essentially for greenfield, we consider cause in the reviewing node, consequences could be anywhere. Yeah. Next is worst case unmitigated consequence. Now, again, there is many a times in the sessions we have gone through, people say we have this safeguard, we have that safeguard, but when you list a consequence, it should be unmitigated consequence, which means there should be no create of any safeguard, and you should look at it as a worst case event that would be possible with that consequence or with that event. So without safeguards to be considered. Next is design review to be avoided. Now, there are several instances where, since in many of the Indian clients, they don't do a design review before 30% HAZOP, many a times that HAZOP session turns out to be a design review. So there, more than looking at the safety aspects of it, we are contemplating or deliberating on the design aspects of the design changes, sometimes even scope changes. I have gone into HAZOPs, 80% HAZOP, where they were discussing the feasibility of a concept. So that is impracticable to do it. You cannot deviate from the safety aspect of it. So that is why I say that design review things should not be discussed in HAZOP. Design related discussions can either be resolved prior to the HAZOP or need to be targeted separately as part of a parking lot item, we call it. Okay. Next is technical inputs, values and ratings based on engineering documents will be considered. As I said, there could be discrepancies in engineering documents. Based on that, then we can see which is the most relevant document and take credit from those engineering values or engineering inputs. Next is alarm controls, interlock safeguards claimed to be validated on engineering documents. Now, these two have to be basically, these need to be validated on engineering documents. Like many a times I go into HAZOPs where the operation says that this is set at this point, this is set at that point, that is the set interlock or failure point or safeguarding trip. But that is not how your system may be defined, may be configured, or how it may be designed for. Your design intent may be something else, but when you do a capacity ramp up or when you do a revamp, you will change the set points. So those set points should not be orally conveyed. These should be documented in some document for future reference, because that operator either his shift can change or the operator can change. But these things should be documented in engineering deliverables, because even if there is a change or there is revamping or there is increase in capacity, so that document will be my basis for consideration of the trips or safeguards. So that is how you need to have them on engineering documents. Next is double jeopardy scenarios to be avoided. Now, this double jeopardy you would have heard it 100 times, but the meaning tends to be different for different clients. Now, double jeopardy, simple definition is concurrent incidence of two independent initiating events or other related failures should not be considered in the HAZOP. Means simultaneous failure. Just to keep it simple, I will tell you how to classify this. Simultaneous failure of two instruments or two safeguards should not be considered. Simultaneous, like two pressure transmitters on the same line, should not be considered, or a control was stuck close with a pressure transmitter failure, it should not be considered. However, you can consider, many clients do consider that operator error could be a failure cause, and then instrument could be failure, and both can occur simultaneously. that is an over conservative approach, but many a times do clients do consider those kind of out of the box approaches. But we do refer to them as double jeopardy and refrain from doing it. But some do insist on that, and then case by case basis, we can look at it separately. Okay, next is HAZOP steps. Again, I've tried to keep this very simple. The first important step is hazard identification based on applicable deviations. You have certain set of deviations mentioned, like flow, like the cause could be flow, cause could be temperature, pressure. The deviation could be more flow, less flow, reversible flow. So basically, that is how you identify an hazard that was possible based on this deviation of the cause, that the cause being the flow. So based on that, you look at applicable cause of the applicable deviation. That could be your more flow, less flow, whatever. Next is the consequences that cause can cause, or what it can lead to, the worst case consequence. Again, you could have 3 or 10 set of consequences. It is good to list all the consequences as per the worst they are impacting for that unit, or you have to list the most what do you call severe consequence. Like, to give you an example, like if you have a flare KOD, you have considered a tank, basically a tank, the vent routed to a flare KOD, and then that going to a flare. Now, when you have basically a overfilling of a tank scenario, you could have an overflow from the tank that could lead to local spillage, which could lead to slip trip hazard or a combustible mixture formation. So that would be a first consequence. And then the second consequence could also be that if the overflow is not adequately sized, then there would be, least resistance could be from the vent flow path, and that could go on to a KOD and then to a flare, which could lead to basically a fireball and a fire rain in your flare. So these are some multiple consequences that can occur, and you have to look at either list all these consequences or look at the worst that can happen. So in my case, in this example, I would prefer to list all the consequences at whichever scenario they are creating an issue. So that should be, or whichever system they are impacting, that should be our approach on listing the consequences. So you could have n number of consequences for the same incident, and you need to list them separately. And again, the consequences should be without the safeguards. How many times have we considered? Inadvertent manual wall. Sorry, we will respond to this queries later in the session. Next is check adequacy of prevalent safeguard. Now, this is an important step. You would have already considered several inherent safety design, inherent safer design measures in your design, or you would have provided adequate safeguards. However, the adequacy of these safeguards need to be evaluated, whether they are adequate based on what is available in the design system, or there is still an incident which is beyond your alarm range. So essentially, in that case, if there is still a need for a safeguard, then you look at recommendations to either eliminate, as we said, the 3 objectives of the HAZOP is to eliminate a risk, reduce a risk, or mitigate a risk. So eliminate basically through inherent safer design, reduce it through logic systems or control systems, or mitigate the risk through recovery barriers. So this is the simple steps of a HAZOP. Yeah, this is how your worksheet looks like. You have your different deviations. Many a times they keep deviations and this different, what do you call, parameters different, like you have more flow separate and then you have more less flow. However, this is just combined for single client. So more flow, more no flow, reverse flow, less pressure, more pressure. That is how your deviations are. Then you list the cause for more flow, whatever your pump overshooting or your duty pump kicking in with the standby pump. So all those things, would be a cause. Next, your consequence would be, what is the worst consequence? Your safeguards, which you have already considered design. Now, based on your consequence, you have obviously considered unmitigated consequence without any safeguards. So based on that unmitigated consequence, what would be the severity of an event? Severity is again a definition based on, it is a client specific definition based on your risk matrix. I will just take you to the risk matrix. So severity could be, see, this is your risk matrix. Okay, now this changes from client to client, location to location, industry to industry. Now what you see here is a 6x5 matrix. Many times it is a 5x5 matrix where you have severity as 5 and consequence or likelihood as 5. So here you have your severity. This is a 6x5 matrix where you have your, again, this was for the Sanlo refinery, so this is a good example. So here you have your 6 phases of severity. You have severity 1, that has no impact. Okay, sorry, this is for reputation, this is for people, this is for environment, this is for asset damage and reputation. Now we look at people because we are looking at the safety aspect of it. Many a times they insist on doing for environmental, asset damage, and reputation together in HAZOP. So that is also there, but let's not complicate it for this session. So you look at severity with zero, basically is no injury to human health. Next is there could be a single injury or health impact for one, then minor injury or health impact for two. Next is, see again you have this definition, what is the moderate damage for an asset. Those things also need to be considered when you define the severity. Next is major injury and health impact, that is severity 3. Permanent total disability or single on-site fatality. Now if you see, in this case the severity from 3 is of major concern, and that is why many a times they consider severity 3 and above, that could be considered for LOPA, because the higher severity scenarios they want them to be addressed, and they need to be as low as reasonably practicable, what we call that as alarm. Okay, so then you have permanent total disability, single fatality, that is severity 4, multiple on-site fatalities and single off-site fatality. Now this is on-site at the plant, there would be several fatalities, and there could be one fatality that is outside of the plant. So that is where you consider 5. And as I said, the community response, or there could be community impact. That is where you have this multiple offsite fatalities, that is multiple fatalities to the people in the community or vicinity of the plant, and then multiple on-site facilities. So that is where you say 6. So this is how you define the severity of an event, that which is also going into your HAZOP worksheet and also your loop. And then you have this likelihood. The likelihood is how frequently this can occur. Okay, so that is how you have this likelihood A, B, C, D, E. Yeah. So that is how you have. See, if you see this is EA is an event that is happening less than 10 raised to minus 4 or 6. Is it 10 raised to minus 6? That means once in 10, so many years. Okay, so that is an event which is less likelihood. Then you have B, which is 10 raised to minus 6 to 10 raised to minus 4 per annum. So then you have C. So you have E, which is saying that more than 1 times per annum. That means this event can happen once every year. Like if you have an maintenance cycle or a unplanned shutdown, but every time this is the unplanned shutdown, this event can happen. So this is the highest likelihood scenario. So based on this, you look at risk or risk matrix based on the severity and the likelihood, and then where you get the risk rank. Like if you have an incident 3 that is happening once in at a C level, so you have your, this is where you have your risk rank. Or you have a D. Typically yellow, orange, and red are considered slightly higher risk. Red is not acceptable risk. Basically, you need to bring it down to an orange or an yellow level, because red is not permissible by a regulatory body or any other statutory organization. This is considered as an higher risk. So you need to provide measures to bring that down either to a yellow, or yellow is more preferable. Orange can be acceptable at certain points based on the management's concurrence, and as long as you're able to demonstrate to the statutory body that the cost benefit analysis, when you do the additional safeguards, that is not viable. In that case, you can demonstrate with the cost benefit analysis to the stipulated body that this is not beneficial. So only then, based on management concurrence, it is acceptable to have an amber or an orange. Otherwise, it is always beneficial to have a yellow or a blue. Many consider the blue as a green, so either yellow, blue, or a green is preferable. So let's go back to the worksheet. Yeah, so this is where you have your severity 1 to 6, as mentioned there, likelihood A to E, and then you have your risk rank based on wherever it falls. So based on this risk ranking is what is of benefit even for the LOPA. So all of these things go into a LOPA study. Many of them you would realize them in the next slides. Next is recommendation. This is where you provide adequate recommendations. Now, whether if you have safeguards or this, then you will look at their integrity or their adequacy. If they are not adequate enough, then you provide further recommendations to bring the system to an alarm stage. Next is the closeout, and this is remarks basically, that is who is going to close out the action. So that is our, yeah, so we are at this 11:15, Shalini. So you want to break now?
Yes, sir, we can take a break. Or if you want to finish HAZOP, like how many slides are left for HAZOP?
No, HAZOP, another 3 slides. After that, we will break. We will Daria. So we will do the HAZOP deliberations, and then we'll directly jump on to LOPA. So we look at. at job deliberations, now comes provided in different ways, but a recommendation should be crisp enough to address the shortcoming, and it should be in such a way that it is a win-win for everybody. So that is why whenever I provide recommendations, I look at the recommendation with these following aspects or approaches. First is every new recommendation needs to be provided considering these aspects. Yeah, it should be technically accurate. That is the most important one. There should be safety emphasizing that the emphasis should be on safety because a solution could be technically right but lacking safety, or it could be the other way around. So first technically accurate, next is emphasizing on safety, next is capex and opex concurrent. Many times we have heard this that you should not be considering the cost in the HAZOP recommendations, but yes, it is always commendable. Like every problem, there could be different solutions, different approaches. So it's always good to look at cost-effective solutions. Like instead of like I would to give an example, many times for a scenario where you have control wall failure, CV failure, I've seen people go ahead with such high PSV setup, then the SIL system setups and everything, and those could be very highly cost impacting and schedule delay. So a better solution I've seen is to have two control walls in series set at the same set point. So that way the cost is reduced, your scheduled delivery is reduced. So you always look at them from that aspect also, and it does a better work because you have your controllability. Even if one fails, it is driving up the root cause of the event, which is control wall failure. So impacting the cause rather than the consequences. So it is important to have those things aspects in mind. Next is schedule driven. Many a times when you go from one SIL level to the other SIL level, the schedule gets impacted by 3 to 6 months. Again, there is a cost impact of 20 to 25%, but schedule is impacted. And remember, the barrels of oil production deferment, that could be a bigger loss when you have 3 or 6 months delay. So it should be also schedule driven. And then there should be minimum downtime or least production losses. Basically, that is another important aspect when you are working in the client side on the operating company. Everything you realize boils down to barrels of oil production loss or production deferment. So looking at those aspects or downtime, it is important. Now you guys have heard of, those who are in piping would have realized there's something called as hot tapping. So hot tapping is also done to avoid these kind of downtimes. So basically those things should be taken into consideration to provide a recommendation to ensure there is the minimum downtime, or you have the things planned for your next immediate planned shutdown. Okay. Next is Okay, next is has jobs suggestions on parking lot items. Now, many times it so happens that we are not able to address all the design aspects in the job, so we park them under parking lot items, and these can be a different variety range. Basically, like in your PNIDs to be reflective, the actual design need to be updated periodically. Many a times I have seen 4 or 5 different revisions. Same it is same A or C revision, and it is at 4 or 5 different dates. So you don't know which of the PNID is valid. So basically, the latest PNID, which is reflective of all the considerations, should be considered based on the changes and other things. Then PNID need to include self-control loops, dotted lines. These are not indicated many times. Then interlock should be well defined. Basically, you have those diamond symbols, or you have your star boxes, other things. And execution of the final element with consistent interlock numbers. Yeah, interlock numbers is very important. Wherever an interlock is generated, that same interlock number should be acting on the corresponding final element. Only then that defines a correct loop, not just for the HAZOP but for automation also. Next is pressure relief valve, rupture disc, and vacuum relief valve. Yeah, I've seen instances where you don't have the set points mentioned on the PNID. That is also wrong, because without the set point, you cannot take real credit of it. That set point is such that it is protecting the weakest link in your loop. So unless you know the set point of the PSV or the rupture disk, how will you know which or ascertain which weak link or the weak equipment it is safeguarding? So those things have to be indicated on the PNID. Next, PNID with all equipment details, capacity, design, operating condition. These again are important because flow-wise, capacity-wise, you would need that data. So PNID should be an holistic document. Like many a times I've heard, like there are instances where a PNID is so well defined that you don't need to refer any document. I have instances where I did not refer cause and effect because the PNID was very well defined. So it should be in such case that everything, it should be holistically inclusive document. That a PNID should be a total document. That is how a PNID should be prepared. Then all tag numbers should be indicated many a times. clients, and it is insisted for regulatory approvals also that you have the right tag numbers insisted or indicated against the right recommendation, because or even in the cause and consequence, because that helps you to avoid this downtime or unnecessary deviation. So you need to have the tag numbers indicated for each tag, which is a cause or an incident or recommendation. Next is process safety information to be readily available. Then the cause and effect, interlock list, description, alarm loop diagrams anywhere. And all equipment data, pump curves, vendor mails to be stored in a repository for reference. Now this is important, as either it is as part of the info pack or as a repository where you can easily access the documents, not just now, but even in the future. Because in the future, you never know which of the documents or which revisions were considered for the HAZOP. So that is very important step. Next is the advantages of HAZOP. Now let's look at the benefits of HAZOP. Obviously, there would be some shortcomings also, but for the timing, let's look at benefit. It provides means to systematically and thoroughly examine a system, process, or a procedure. Then it involves a multidisciplinary team, including those with real-life operational experience and those who may have to carry out the rectification process. So basically, it is looking at the fag end of the users who are at the receiving end of any incident or anything. So they are the ones who we are targeting to by doing these HAZOPs as inherently safe. Next is generate solutions and risk treatment actions. So coming out of an HAZOP, you have your specific recommendation, specific solution, and the recuperative action associated with it. So it is very specific approach. So that is a benefit of an HAZOP study and exercise. It is available to a wide range of systems, processes, and procedures. It allows explicit consideration of the causes and consequences of human error also. It creates a written record of the process which can be used to demonstrate due diligence for any statutory or regulatory approval. It has reports are leveraged to seek statutory approvals from concerned authority and environmental regulatory bodies. Next is the limitations of HAZOP. Like everything has its benefits, there are certain limitations also. A detailed analysis can be very time consuming and therefore expensive. Obviously, gravitating so many resources or converging of so many resources at a single forum, including the HAZOP, Scribe, and other SMEs, that could be cost expensive. So that is why we say it is cost expensive for longer time consuming sessions. A detailed analysis requires a high level of documentation of process or system and procedure specifications. Obviously, you need a lot of systems, a lot of things defined, well-defined procedures, SOPs, and other things. If you have to do a very inherently perfect HAZOP or that could be time-consuming and more documented-driven. Now, it is constrained by draft design and design intent and the scope and objectives given to them. Yeah, many a times it is restricted by the specific objective. Like if it is a management of change, they are looking at only that part of the design, or if it's a brownfield modification, they're only looking at that aspect of design. So many times it is constrained by that design intent. Like the process relies heavily on the expertise of designer, who may find it difficult to sufficiently objective to seek problem. This is what happens when many a times when they are in a forum, especially the process leader or SME, they are the ones who have designed it, the system, and they find it, or they are reluctant to accept any recommendation or any action because they consider it as a shortcoming in the design. But that is not a case. It is actually a complementary exercise to your design. So for any process people or process leads who are in the forum, remember that a HAZOP is an exercise of revalidation of what you've done very well, and where there are gaps, we just have to address that. So always take it in your benefit to take any actions or any recommendations, because that is complementing your design to ensure that you are holistically addressing any gaps or errors. Yeah. Next, HAZOP is not a design review but a safety review. As such, design-related actions should be taken separately as part of parking lot items. Again, we've discussed this. HAZOP should not take care of design or concept of these. Okay, next we move on to LOPA. So now, as we said, we are required to do certain LOPA screening, and this is because not all the HAZOP recommendations would fall under a LOPA. There are several HAZOP recommendations which are driven by the severity of an event or by the nature of which that incident can occur, and only those should go for a LOPA session. So actually, we are starting the LOPA here at 11:43, and so basically we'll just go through the screening part, okay, where we have LOPA screen for qualifying exclusion scenarios. Now, first we look at the qualifying scenarios, means which scenarios actually qualify and they can be considered under LOPA analysis. So not all severity scenarios qualify LOPA. Only the high severities of critical HAZOP scenarios may be analyzed further for LOPA. Now, what scenarios would you like to consider for LOPA is again a subjective study based on the client requirements. However, many clients, wherever there is an orange or a red scenario in the severity, everything above that is considered for LOPA. Like in this case, if you see, a 3 is basically something which is having a major injury or a health. Some clients may also consider that injury is not a LOPA scenario, but any fatality could go up for LOPA. So they can consider either starting from a 3 severity as a LOPA or a 4 severity as LOPA. So then 3, 4, 5, 6, all of these which are in red will fall under a LOPA evaluation or a LOPA qualifying scenario. Yeah. So based on the risk matrix, like for a 5x5 risk matrix, essentially the severity 3 and above, and for a 6x6 risk matrix, essentially 4.5 above or higher scenarios are considered for LOPA. So that is what your definition of severity. Now again, this is the first instance where we are using the HAZOP evaluated data for LOPA, where basically we looked at the consequence of HAZOP and then we determined its severity, and then we are considering this severity and above severities for LOPA's analysis or LOPA qualifying. Next is some clients insist on all orange or red risk outcomes to be considered for conservative LOPA analysis. Again, this can lead to prolonged LOPA sessions and drain of exorbitant resources. Like if you say the rates of a LOPA chairman are slightly higher, or a SIL assessment or SIL determination chairman are slightly higher than the HAZOP chairman. So looking at the resource exorbitance, you are unnecessarily engaging these resources if you're looking at an overtly conservative approach of having all the ratings in an arrest also evaluated. Here, clients look at it which go into a LOPA qualifying scenario. Okay. Next one is exclusion scenarios. Now, this is a very important aspect of LOPA. Many people tend to miss this part, and then they keep, fiddling with the LOPA exercise, and they reach inconclusive analysis, or they keep discussing on different tangents, but there is no conclusion to the discussion because they have not done this screening exercise upfront. When you do a screening exercise upfront, when you do this qualifying scenario, if you look at these exclusions, these are also part of the qualifying scenarios. So maybe this is in more detail, and that would help you to evaluate which scenarios we do not consider for LOPA. Okay. So scenarios initiated or addressed by high-risk work programs. Like those who have worked on the manufacturing or operation side would know that there are certain high-risk activities that require permit to work or your job safety analysis, JSA as they call it. So those activities are already done under a separate supervision, under separate permit work, and under separate, buddy system. Many a times they do it under buddy system. So those activities essentially we do not consider in LOPA. Many a times human errors and other things are also not part of the LOPA exercise. So which are those exclusion activities? Like you have an hazardous energy control exercise or an electrical safety work that is to be done. Yeah, there is no proper guidelines, right? But this is based on the different clients I have worked with, and they had their different specific guidelines for exclusions. And this is what basically, it is a compilation of at least 4 to 5 clients who have a different set of guidelines for LOPA screening. And having worked with them, I was able to readily extract from those this. Yeah. So next is open flame hot work. That is also not part of LOPA because that is done under JSA. Line breaking, if you are breaking a live line or even a closed shutdown line, that is not part of LOPA. Confined space entry is not part of LOPA. Then elevated work or fall protection. Now this is typically part of human factor engineering or HFE or ergonomic study, whereby so just going by HAZOP severity, you would have so many scenarios. Like I can tell you that there would be at least 4 to 5 times scenario which would actually qualify for LOPA if you just go with the severity. So just going by severity doesn't help your cause because you would be evaluating unwanted scenarios. Like if you look at this list, probably you'll understand why I'm emphasizing on it. Next is elevated work fall protection is part of against scaffolding and different ergonomics activity. Mobile crane work or evacuation and trenching, power in industrial trucks, or overhead hoist and stands. All these things are part of different job safety analysis or permit to work. So it is not part of LOPA screening. Next is screening that scenarios that cannot be processed, that are not process dependent but are machinery related. Like many a times you have certain machinery packages which have their own set of guidewords and safety assessment. So that cannot be combined with the LOPA because they first of all, any recommendations you make, they will not be, or they will not be obliging to your recommendations. they may be reluctant to take any safeguards, and they have their own safety methods like machinery safety assessment. I think just prior to this session of learning, there was a machine safety done by Mr. Naran, and I think that was a good guidelines for machine safety review, which is again excluded in LOPA. Next is scenarios where spontaneous equipment or pipe integrity failures to the environment is the cause. Now you have catastrophic failures or pipe rupture scenarios or all those exchanger rupture scenarios which we do not consider. These are promoted or these are because of material or construction defects or fatigue or corrosion, erosion, and which are best prevented through proper design to standards, or they're evaluated through a QRA, that is a quantitative risk assessment. Okay, or a consequence modeling. Basically, you do consequence or a physical effect modeling or a dispersion analysis in many of the hazardous gases cases. So these such things which cannot be considered in LOPA, there is a separate study for that. Even fault tree analysis is used. Next is human error initiating event during the transient mode of operation, such as you have different modes of operation. Like during startup, there would be a different set of human or SOPs required or a checklist required, and that is why these human errors during these modes of transient operation are not considered LOPA. Like you have transient modes of startup, shutdown, or maintenance mode, even turn down mode, like which often depends heavily on the package design and the operational discipline and administrative controls. Administrative control is a very important thing. Like I said, the checklist or the SOPs, or you have double double supervision, or sometimes they call it as in pharma. I think there is some specific word for that. Supervisory control of any activity or any task. So in such administrative controls, we don't do it. Like example for that is the drain vent wall inadvertently left open on startup. Now there is no means of doing a LOPA for this. When you have a drain or a vent wall left open on startup, obviously it has to be flanched, it has to be blinded off. But those are part of an SOP activity which have to be done, or they are job safety analysis which is required to be done. Next is non-specific causes, such as like you need to have a specific cause for a LOPA. Like many times there are instances where you have low flow from upstream or no flow from upstream. So those causes you cannot deliberate on because you don't know what the cause is from the upstream. So you need to have that specific cause, like a control valve stuck closed or anything of that sort. Then you can look at it as a LOPA scenario. Next is consequence, which would be normally be addressed as part of a hazardous area classification or ATEX study. Again, like we said, there are different studies: QRA, ETA, hazardous area, ATEX studies. So these refer to different aspects, like you have dust explosion or you have hazardous chemical explosion. So those are dealt separately. So they are not part of a LOPA study. The natural disasters, very important natural disasters. Some sites are vulnerable to volcanoes, all those different we are seeing right now in Indonesia and Japan. So those things cannot be quantified in the LOPA. Next is act of terrorism. Now that is with all these refineries summited in the past 1 month, there have been 12 instances. So you never know what those could be, vulnerable. So these acts of terrorism or anything, I'm not speculating that they are act of terrorism, but such instances where there are act of terrorism involved, or the flight crashing into some refinery, or those what you call the drones, that those cannot be really contemplated or speculated to be part of a LOPA activity. Acts of sabotage is another important thing. Of late, there have been several instances where there are acts of sabotage which are not part or cannot be considered. Next is external events like a plant failure, a plant fire, or an extreme weather. Both of these are not considered because for fire there's a different set of guidelines as per NFPA, and that is what is the driver for this, and they are not part of typical HAZOPs or LOPA scenarios, because HAZOPs and this deal with the internal process aspect of it. So external fires are not considered in such scenarios, or extreme weathers, because if you see in temperature, like I'm not sure if you've seen on YouTube, like in Kuwait, when the temperature crosses 60 or 55 or 60 degrees, just because of rustling of leaves or dry leaves, there is fire. And I've seen that severely occur at site. So those things are external weather impacts which you can never contemplate, or how they can, form as an incident. Next, the following equipment and packages which are designed, built, and installed and maintained to correspondent applicable stringent industry codes or standards of regulatory requirements. These again do not fall under ROPA, like they have burner management systems. So for a burner management system, they have their different set of controls. They have different set of PMS, PLCs, and PMS, ESDs, and other things. So these are typically designed for stringent standards. They are inherently safely designed systems, and those we do not consider in the LOPA, because even invariably, whenever they're integrating a system, many times the LOPA or HAZOP recommendations are not essentially taken care by these vendors. Like you have the autoclave, mostly in pharma and biotech industries. our vendor specific packages, their interconnections, vendor specific package, again, when I say that they have their own system of evaluating the safety of the system, and they many a times they do comply, but if they aren't complying, then we do typically leave that as a separate entity, and then we try to integrate it. And wherever we are integrating the interconnections, we look at them with regards to HAZOP and LOPA. Okay, so with regards to that, we have done the screening. I think those of who just raised an apprehension that they do not have any standards for the LOPA screening can leverage this worksheet in the future to screen out any systems or LOPA exclusions in their studies. Okay, moving on. Next is LOPA and SIL assessment. Okay, now I would request you all to be really attentive, because this is the main crux of our study. And the whole, I think HAZOP is very generic. People would have gone through HAZOP sessions and earlier trainings, but LOPA would be very, very skillful approach. So let's look at the definition. LOPA is a very structured approach or a technique or a tool. Basically, it is referred to as quantitative tool. So to demonstrate that the existing level of risk is tolerable, if as low as reasonably practicable. So you guys have heard of alarm as low as reasonably practicable. Many times client refer to as, some clients refer to as risk if tolerable. The risk is tolerable is if as low as reasonably practicable. So that is why I call it TIF alarm. When taking into existing account of the existing barriers that are already provided to the design. Next, to identify the risk reduction requirements with respect to people, asset, environment, and reputation. And then look at the safety integrity level or the SIL determination and assessment. So that is an important outcome which comes out of a LOPA study, is a SIL determination or a SIL assessment. So which gives you what level of SIL is required to ensure the holistic safety of a system. So that is what is the definition of LOPA. Next, like there are governing standards. I said IEC 6155, which is a functional safety that is used for HAZOP as well as LOPA. Next, there's a separate IEC 61508 that is basically for functional safety of electronics, the programmable part of the logic solvers and other things. So these are part of the electrical safety. Next is important definitions. Now, with regards to HAZOP, we were able to look at the generic definitions because we are more or less aware of it. But when we come to LOPA, there are certain definitions which are the drivers to determine the safety level or to look at enhanced safety. So I want you guys to be exposed to these definitions, and please be with me. So we look at it meticulously, because these will be our drivers in the next following slides. First is a SIS system, basically a safety instrumented system. This is comprising of a sensing element, a communication element, and a final element. Like a sensing element example would be pressure transmitter, level transmitter, flow transmitter, temperature transmitter, a logic solver which comprises of a DCS or PLC system, or even your BPCS in some cases, like your burner management system use BPCS for triggering many times. And your final element, which could be an ESD and an FNG activation. So that is how you look at a whole holistic system comprising of a sensing element, a logic solver, and a final element. Next is common cause failure. Now, basically in these systems or the SIS systems, there could be common cause failure. Like if the system is typically catering to incidents, there could be a common cause that could be leading failure of both the loops. So that is what we call it as a concurrent failure of different devices resulting from a single element, where these failures are not consequences of each other. Means they are independent consequences, but there could be in the common system in a single event, due to single event. Okay. So next is enabling condition. Again, this is a condition that is not a failure. It is an error or a protection layer, but makes it possible for an incident sequence to proceed to a consequence of concern. Like this may not be an essential an event, but it is an enabling event, means an event that could lead to a consequence or due to which there could be a consequence. Yeah, so that is what we call as an enabling event or enabling condition. Next is conditional modifiers. Now, conditional modifiers are very important parameters in our system which reduce the consequence or likelihood of the system. The conditional modifiers are conditions that must be true for the hazardous events to be fully developed and are generally associated with post-release part of an incident or a consequence. Now, for examples of this would be probability of personal presence or occupancy in the unit. Now, let's suppose you're looking at a certain unit. It may so happen that the person is actually seated in the DCS room. Okay, enabling event example is one when we go to this. We are going to look at three scenarios, industrial scenarios, where we have considered these enabling events, and I think that is the best way. So you will be able to correlate with the enabling condition. So yeah, probability of personnel occupancy means in that plant many a times the operator may be seated in the DCS or a central room, and he may not be in the area or the vicinity where this incident is occurring. So that is why you consider this as occupancy. Remember, I give you an example where we said that the platform will only occupy 52 days in a year. So here its occupancy is almost 52 upon 365. So that factor is only what is the vulnerability to the operator. So that is how you look at an occupancy. Next is probability of an ignition. So it may so happen that that place or there, though all the equipments considered there would be rated or X-rated or ATX rated. So essentially, they may not be providing that external source. Like when you look at a fire triangle, you need your fuel, you need your air, and you need an ignition source. So basically, you cut off any of the single side of the triangle, and then you are able to ensure that there could not be a fire. So in this case, that ignition basically could be created, removed either by having ATEX equipment, or there are no trucks or anything flying in that vicinity. So the trucks or usually vehicles flying in that locality or around that unit could also be a major source of ignition. Or if there is lightning, that lightning could be a major source of ignition. So when you look at lightning arresters or earthings, so you can take credit of that. So all these are probability of ignitions. Next, probability of explosions. Again, see, when you have as per the fire triangle, you have a fuel, you have an air, and you have an ignition. But suppose your fuel itself is not within the concentrations of LEL to HCl, so that prevents your explosion or your flammability mixture being in that explosive range. So that is your probability of ignition. Basically, you have to ascertain whether that fuel leak or any catastrophic rupture is leading to an explosive mixture within its range. So that is your probability of explosion. Many times that may not happen because if the hairline leak or minor leak, plus with air exchange ratios, and many times there are air exchange ratios. So this you can leverage as a credit to establish that there is lesser probability of ignition or explosion. Next is probability of equipment damage or other finance. Yeah, many times it may so happen that there could be a fire. Like a typical example would be a deflagration event. When there is a possibility of fire, but the fire formed is not able to sustain within that equipment due to whatever, whether there is no adequate fuel or there is no, like when we do the examples, you would realize that there was some deflagration scenario, if I can recollect right. So there you would realize that there is an equipment damage, but it could not be to an extent whereby it could have been through a full fire or a full explosion. So that equipment damage could be limited only to some leak points or to some what do you call flanges or some packings only. So that is where you look at that probability of equipment damage or financial impact. Financial impact could be minimal; it may not be of the full equipment. So that is what we leverage as conditional modifiers when we look at the LOPA of an incident. So yeah, next let's look at the other definition. Yeah. So now we look at this TMEL, which is a target mitigated event likelihood. Now, this is a definition as per OSHA or UK guidelines. And mostly, I think because many people refer to this OSHA guidelines, Purple Book, or all those things. So typically, these are more or less used as guidelines for setting this TMEL, and that could vary based on client requirements or client guidelines also. However, for this discussion, let us look at this chart, which is based on RAM severity. So remember the RAM risk assessment matrix we discussed a couple of slides before, and there we discussed at a severity of 3, 4, 5, and 6 based on the red color. Okay. So based on these rank severities, we are leveraging again this from the HAZOP to determine what impact it can have on the safety aspect to the personnel, or even like this is for the person, it could be for the asset also, but here it is for the safety study, though they wanted it limited to the personnel. So here you will see it could be major injury or health impact affecting worker performance in long term, such as absence from work for more than 5 days, or affecting daily life activities for more than 5 days, or irreversible damage to health. That could be like any thing that is lung impact, lung fibrosis, all those things, or even injury or permanent disability. So those things we would look at it as a target mitigated event likelihood, that is 1 into 10 raised to minus 4 per year. Okay. So this is what is defined by OSHA. So for this severity, this is the TMEL. this is what goes directly into a LOPA based on this severity category, and this value is directly going into a LOPA. So based on whichever severity and incident. For a severity 4, it says single EOUK permanent total disability, that is, or a fatality resulting from the injury. So see here it is considering permanent disability or a fatality resulting from injury or occupational illness. This is 1 into 10 raised to minus 5 per year. Similarly, for multiple, I am sharing the PPT. And can you just re-log in to check why you are not able to see the PPT? Because I think others should not have had the concern there. They are able to see the PPT. In fact, if you have logged off for the break or you left the session, there could be issues. So please rejoin. Okay, next is so there's multiple fatalities. That is correct. Thank you. So next is multiple EOUK. So you can have 2 to 10 deaths or a single public fatality. So resulting from injury or occupation. So this is again grave where you have 2 to 10 deaths within the facility or a single public fatality who are out of the facility and they have not subscribed to the danger or risk. There is a single fatality there. So it is 1 into 10 raised to 6. That means 10 raised to 6 per year. That means at least 1 in a million persons should not have this fatality. Like, there should not be more than 1 in a million fatalities in a whole year. That is what it means, to say it simply. Okay. Next is multiple public fatalities or multiple UK fatalities. That is 11 or more resulting from a single event. This is typically mean that the community, that is out of the people living out of the facility, they are exposed directly, and the direct impact leads to 11 fatalities. So that should not be more than 1 in 10 million. So that is what per year. That is 1 in 10 million is not is the maximum acceptable limit. When you say acceptable limit means it is just a benchmark or a threshold. That means this doesn't define this. No, OSHA guidelines in India. India has a different set of guidelines for their own review. That is morely client specific driven. So anyway, we will be looking at these target mitigated events because these are the values which will be checked based on whatever safeguards we have. As long as we are meeting these values or we are lesser than these values, we are fine. If at any point we are crossing these values, then there is a need for additional safeguards. So of the 3 examples which I have considered for analysis, we have one case where you have exactly meeting this value, one case where you are below this value, and one case where you are above this value. So we will look at them and deliberate. So stay with me, stay connected for the rest of the slides, and you would be able to differentiate how exactly or how they deal and how you are able to analyze them. Okay. So this is the definition for target mitigated event likelihood, very important factor for our loop analysis. Okay, next is safety instrumented function time. Now, yeah, my pleasure sharing knowledge. In fact, we have to thank Yashpal ji for his Pathshala because he's been doing a great noble work of propagating this knowledge at free of cost. And the best part I've seen in my industrial experience all these years is many a times we as starters or we as initial early careers, we go for the certification part without actually knowing the knowledge or part about it. So it is, I think, the good part about this exercise is that HSC RMS is not just providing you the information, but they are also providing you the certifications and with the accreditation, of course. So I've had instances from different, don't want to name the accreditation bodies, but they had approached me saying that you have all the prerequisite knowledge and everything. We will just charge you for the certifications. And the certifications cost were absolutely exorbitant, $1,200, $1,500 just for the sake of certificate. And that is when even I realized that certification is not important, the knowledge is important. And that is why we converged on, or we agreed that we will do this, free training experience for the benefit of all the folks or the young careers or, even mid careers, late career guys who are desperate in seeking the information. They want the knowledge, they want this, but many times they don't have the time or the financial resources to do that, or many times it doesn't break even with the certification cost and other things. So yeah, I think the credit of this training should be to the HSC RMS team as well. Thank you very much. Okay, so next is safety instrumented function, SIF time. Now this, many of us, SIF time and process safety times are 2 parameters which many of us in the design as a safety consultant or as a even process designer, we miss these aspects. So these are two factors. One is safety instrumented function time, and then the next one we will see is the process safety time. So these things have to be inherently designed such that our system can respond within these times. Okay. Now, if you look at a SIF time, means represent the actual response on process safety. Yes, I have the next slide is process safety time. So SIF time represents the actual response time of the safety instrument system. Like looking at a SIS, as I told you, is a system comprising of a sensor, logic solver, and final element. So the total cumulative time, all these three components, along with their software and hardware, okay, they require to respond is called as the SIF time. Okay, this is the time they require to detect, decide, and act to bring the process back to a safe state. Now you look at it, each element of this has its own sensitivity, accuracy, a response time. So all of these together, for each element, for each communication, that means a soft link between a sensing element to a logic solver, then the soft link between a logic solver to a final element, those soft links, or an hardwired link to any of the final element. So all of these, do they have that adequate or times, or the cumulative time is what is called as safety instrumented function time, SIF time. And we'll see how it is important with regards to process safety time in the next slide. Okay. Next is PFD average. Is the probability of failure on demand average. Means like what is the probability that an instrument or instrumented function or a penultimate safeguard will fail or will fail on demand, or what is that average PFD failure, and RRF, that is the risk reduction achieved with this PFD failure. Now, if you look at it, probability of failure on demand means the definition itself says that when you need a demand, how vulnerable is this instrument to failure, or what is the probability that it can fail? That is what is defined as part of our SIL definition. SIL 1, 2, 3, 4. You define that. That is where you all get this probability of failure on demand. Okay, and then various risk reduction. Now, based on each safeguard you consider, you have a certain level of risk reduction. Okay, and then that is what is providing various design measures and safety considered. Now, refer next table for PFD and risk reduction. So, I'll give you the table for different PFD and risk reductions. However, just remember the definition is PFD average is equal to 1 upon risk reduction, or the other way around, the risk reduction is 1 upon the PFD average. Yeah, so if you look at this is again a well compiled this data for PFD or generic PFDs, or see again when there are generic PFDs, that some clients may defer to take different risk reduction credits, or they would like to have it differently. But this is a data bank as per CCPS, and it is again HSC RMS data bank, which basically defines. I've only picked these 12 which were relevant, or there are others based on each loop. There were more than 50 or 100 examples of that. So anyway, so if you look at overflow line with no impediment to flow. Now, if there's an overflow to a tank, so essentially that is considered as a free flow path for any overfilling scenario. And essentially when it is sent to a drain, that means it is sent to a closed drain system, which is again in intrinsically safe design. So in such case, where you have an overflow without any impediment could be a U loop inside of overflow, or it could be a seal at the end of the overflow. You could have, you have these liquid seals at the end of the overflow. So those could be impediments. So without that impediment, if you have a system or an overflow, you can take credit of it up to 1,000. You see, it can give you a risk reduction of up to 1,000. Whereas if you look at the PFD average, it is 0.001. That means 10 raised to minus 3. So 1 upon 10 raised to 3. That means 10 raised to minus 3 is the credit you get. Similarly, an overflow line containing a passive fluid or with a ruptured disc, basically you have a liquid seal, and many times you have that sealing fluid, and you can have the ruptured disc also in some instances. So in that case, this risk reduction is only 100, or it is generic PFD of 0.0 or 10 raised to minus 2. Okay. Next is line containing a fluid with the potential to freeze. Now, many a times, obviously in India, there is lesser scenarios, maybe in North, but in some areas like in UK and other places, you have, or even, Russia, Kazakhstan, those places it goes to minus 60, minus 65 degrees where the plants are operating. So in these cases, if there is a freezing possibility, in that case, then that safeguard itself is made redundant. Because when there is freezing, there could not be overflow. The line would be choked up in the overflow choke point, and then the overflow or the spill inventory will not be sent to the drain system. However, they do target or they do attack such scenarios with steam tracing or electrical tracing of the whole overflow lines. But invariably, even with the tracing, in such case, if you are taking credit of that overflow line, it will be only 10 risk reduction, which is 0.1 or 10 raised to minus 1. Okay. Next, we have dikes. Again, dikes, the bunds are part of design safety. So we are taking credit of 10 for them because they are ensuring adequate design or prevention of further catastrophic event. Similarly, drain to dikes, pumps, all those things, we have taken 100 because they are basically mechanical devices. And then permanent mechanical stop that limits the travel. Now, this can be considered in case of control walls or, certain big walls where if you have a mechanical stopper, that stopper credit can be taken as 100. Like if you look at an actuator stem of a control wall, there are instances where you provide a mechanical stopper to them. So in such cases, you can take credit of 100 risk reduction. Safety control loop, which is again, as we say, the sys loop. For every sys loop, you can take credit of 10. If there is a safety interlock which is not SIL rated, you can take a credit of 10. Then if you have a sys loop, which is one loop, you can take credit of 10. If you have two loops, you can take credit of 100. Then if you have sys 3 loops, you can take credit of 1000. And then for sys loop, you have credit of 10,000. But essentially, people don't typically consider these 4 sys loop, or it could be complex design. And then you have the next systems where you have similarly where you have sys 1 loop, you could have SIL 1 as the SIL 1 rated system where you can take credit of 10. Or let's go to the definition. I think that would make it easier. So here you could have the SIL 1 loop. There they were saying number of loops, whereas here you are saying certification or rating of each loop. So here you can say SIL integrity levels. It is integrity level. Okay, my apologies. I think we'll go slow. So we look at this integrity loop. So I think this definition you would have had it 100 times or seen multiple times on the internet for the SIP. So I would let you guys take a couple of minutes to absorb and assimilate what this definition and try to interpret it, and then I will explain to you. Sorry, I drank water with the camera on. Okay, so integrity level is basically is a integrity level of a function shall be defined by calculating the PFD average of the function. Means, don't get into the definition part. Integrity level means how well is the integrity of that instrument to respond whenever there is probability of failure on demand. Means whenever there is an incident, how fast, how well that equipped power instrument or safeguard can respond. That is a simple definition. Now, there are definitions for SIL. See, first is no SIL or no integrity level, that is just a basic safeguard. You consider that as a simple one, or you get a risk reduction of just simple, that is as good as no risk reduction. Then SIL ILA, this is something they have introduced intermediate, that this was client specific. But yes, if they have a benefit of risk reduction from 1 to 10, they are considered as a SIL ILA. I think for one of the cases we have taken this, we'll have to look at the Excel files. Next is IL1. Basically, this is SIL 1, SIL integrity level 1. So for this, if you look at it, you get a risk reduction of 10 to 100. Suppose you have an instrumented. Now again, when you say SIL 1 or SIL 2 or SIL 3, it should not be that just the components or the sensing element, final element, or the logic solver are rated for SIL 1, SIL 2, or SIL 3. See, when you say a SIS is a SIL 2 or a SIL 3 or SIL 1, it means that every component is rated for SIL 1, SIL 2, or whatever SIL 3. Every component, the sensing element, the logic, and the final element, or the soft links. And these system holistically, this SIS should demonstrate that it works as a SIL 1 or a SIL 2 or a SIL 3 instrument. So it is not just the individual components or they are rating, but they should actually work or function as a full SIL 2 or SIL whatever SIL rating it is credited for. So that is only possible, or only if that is there, that all of this work in cohesion as a single entity, demonstrating that they are rated for SIL 1. So then we can take credit for 10 to 100 reduction, or they give you a PFD of 10 raised to minus 1 to 10 raised to minus 2. Similarly, for a SIL 2, it would be, see, it is simple. If you say SIL 2, you go to the risk reduction, it is 100 to 1000. So that to remember for future references or anywhere in your life, because these are interview questions, this will definitely come up in most of the interviews. So the easy part is remembering SIL 2. Okay, SIL 2 means 2 decimals, that is 100 to 1000. as a risk reduction. You reverse this 1 upon risk reduction is what you get is PMT average. So that is the best way of remembering. Similarly for SIL 3, it is 1000 to 10,000. You reverse it, you get 1 upon this, that is the risk reduction, or you get the PMT average. Now, many a times in our system, like when I'm saying our systems means let us confine ourselves to oil and gas, fertilizers, pharmaceutical, pulp and papers, metal industries, or even other cement and other industries. We typically try to limit our design to SIL 3 systems because I'll tell you the reason. Many of you may tell you why they limit it, but they don't give you the reason why they limit it. Yeah, that we in our instance, in one example, we are getting exactly 10 raised to 3, and I will tell you where we will take that or where is the reduction. So, okay, so where was I? Sorry, so yeah. So many a times you would see this definition, they will ask you or they may tell you that this is the definition. But when we go to SIL 4, there is a strict driver from the management and from the many a times even the country wise that they don't consider this in our sectors. However, SIL 4 system designs are still considered nuclear sectors because there it makes cost benefit or it makes sense to have SIL 4 system looking at the catastrophe they can create. Plus, these systems still make it viable design. So whereas when we have SIL 3 in our oil and gas, fertilizers, pharma, downstream refineries and everything, there is a directive not to go for SIL 4. Whereas relook at the possibility of reducing the SIL or ALAP level through additional safeguards, or they insist on providing or relooking at the design aspects of it. Revisit the design and try to reach the ALAP region through design changes rather than going for a SIL level. And the rationale for that is whenever you go from one SIL to another SIL, you actually go from a cost increases 25%. So imagine, you have a 25% cost increase here, then you have a 25% here. So basically you are having a 100% cost increase from this level to this level, this level to this. You have a 100% cost. That means where your plant was supposed to be 5 million, you are based on this, it is already inflating your cost by 100%. So essentially in that case, that is why in our oil and gas systems, they insist on relooking at the design and not going for such high level integrated SIL 4 systems. I would suspect you guys would have encountered any of those unless you are in a nuclear setup. Okay. So yeah, this is the definition of SIL or integrity levels. Okay, now the important fact where I was saying the process safety time. So I would request you to pay double attention for this process safety time because this is the driver, and as a designer or as a consultant, we are supposed to deal or we are supposed to look at all our safeguards with regards to this process safety time. Now, PST, just going by definition, I will brief you through the Excel file. PST is the maximum time available between the moment a hazard deviation begins. That means the moment your operating envelope is lost or the parameters are moving out of an operating envelope to a point at which the system reaches a dangerous state. So that means this is the time you have from the parameters offset from an operating envelope or your controls failure to a point where there can be a hazardous event. That is the whole time range is called as a process safety time. So it defines how fast a protection layer must react to prevent escalation. Now this is where you compare it with the safe time. However, before that, I want you to look at this graph. By any means, it is possible to zoom in this, Shalini. I hope you guys are able to see that. So, okay, let me try to do it here itself. Okay, so if you look at the small square to the left, that is close to your on the 0 on the x and y axis, that is which is your operating time or operating envelope. The moment the blue line you see, that is progressively increases. That is the deviation is moving towards a catastrophic event. So if you look at the process safety definition to the bottom, it is process safety time. It is as defined by IEC 6155. It is the total time, that is the sum of TI, T0 and TP. Basically, it is the early response time. Early response means wherever you have set your alarms, your controls based on your FC, PC and other things. So you've set those alarms for that parameter to be reset or brought back into the operating envelope. So this is where you have set that alarm. So this is your early response time. So your process safety time is the sum of this time plus your operator reactor time. Now, many a times, as I told you, the operator has a certain time to react, and this is only possible if the operator is continuously available in the facility and is in the vicinity adequately located for him to respond. Plus, he's been trained. That means you need to have skilled operators who are able to take the recuperative action in a timely manner. So that is where you have this operator time, and this is basically from your PAH to PAHH, where you have this leverage for the operator to reset that whatever or troubleshoot it and then reset the parameter back to the operating envelope. So that is where is your operator time. And the third and the most important is your safety instrumented function set point. So this is the point where your SIF system or your safety instrument system will automatically initiate. So this is the time where you have your SIS time, that is your safety instrument time, up to a time where your this is your penultimate safeguard, and from the penultimate safeguard to the ultimate safeguard. So this is the last time, that is your SIF response time. Basically, your SIF response will occur in this time, and at this point, your pressure safety wall or your mechanical safeguards will come into picture. So your process safety time basically is the time from this event to a catastrophic event. However, because of the mechanical safeguards, we are referring this to as a mechanical safeguard, or you see it is called hazardous event. Okay, if a pressure exceeds certain design pressure. So here is where you have your typical PSVs or rupture is set. So basically, this time, between this time to this time, is your total process safety time. That is a total of your early response time based on your controls, then your operator intervention time, and then based on your SIF response time. Now, the most important part of this discussion is that your SIF response time, usually this SIF time should be lesser than the process safety time, which is actually common sense. But many a times, I've seen systems that are faultily designed because your SIF time response could be higher. It could be so many a times their argument is, sir, we wanted a SIL 1 system, but we are providing SIL 3 system. But that doesn't mean that the response time is adequate. Your SIL 3 system would be dysfunctional or redundant if you don't have the prerequisite SIF response time. SIF response time corresponding to lesser than the process safety time. So that is the main checkpoint or validation required by all designers, all engineers, or safety consultants whenever you provide any process safety device. So here it is immaterial of the SIL level, because the SIL level could still be there, but it could have a considerable delay in responding. Then it is of no use to have that safeguard essentially. So this PS maximum event response time, maybe in the future, yes. So basically, this is what is our process safety time. Can you please explain again SIL 1, SIL 2 with examples? Okay, how can we quantify SIL? Yeah, quantify this is what is difficult to quantify based on your time. Your control wall has a certain time. Then your operator response is given. Maybe now first you calculate a process safety time from this event. Suppose you have 30 minutes that this event can go to from an offset position to a incident level or to a PSV pop-up. So within that means you have 30 minutes of time. Now many a times, just to give an example, it is said that the operator is required minimum 15 minutes to respond. Invariably, that is the benchmarking I've seen in many industries, that they consider at least 15 minutes for the operator to respond from his DCS room, understand the fault error, and then go and respond to it. So all those things minutes. And essentially, early response time is maybe you guys would have considered, from going from a level high to a level high, or in the tank. So you would have considered certain residence time or certain based on the working volume of the tank. That would be your high time. So that is where you have your early response time from an L to an LAH to an L to an LAH. That would be your early response time. And then you have your this time, which is your H to HH, from an LAH to an LAHH. This is where you have your this SIF response time, or you also call it as a time to an event, whereby your event could be overflow from the vent or spillover, or overflow from your designated overflow. So that is your time. So basically, consider this would be as 5 minutes. This was 15 minutes, and suppose this was another 5 minutes. So this is a total of 25 minutes. So if that is lesser than this 30 minutes, then we are able, and then the system is inherently well designed or safely designed. However, if this any of these times are offset and it crosses the 30 minutes benchmark, then your system is inadequately designed irrespective of whatever integrity levels you are providing. And looking at the integrated definitions, I think it would be more relevant once we look at the example. If you want, I can go back to the slide, but again, it would be lost trying to look at just these without understanding or how to interpret them. But for the time being, you just remember SIL 2 is 10, 100 to 1000, SIL 3 is 1000 to 10,000, SIL 4 is this. Okay, and then we will relook at, or we have to refer this table back when we are doing the exercise. Okay, next, I want you to understand the importance of this, we call safety process, safety time. That is why I've had a separate slide just to understand. Because unless you understand the rationale behind why it is required or the significance, we will not be able to make justified decisions. And not many in the industry would explain you this because it is not readily available. You will have to have bits and pieces referred from different references and standards. So, okay, the significance of a PST in process safety design. First is they ensure proper design of the safety layers. Okay, that is what we have seen in the graph. They verify that the SIF can act without the within the PST to avoid loss of containment, fire, explosion, or an equipment damage. So again, that is the whole objective of designing a SIS, is that they act within the process safety time so that to ensure that event doesn't go to a hazardous level. Next is they guide engineers in selecting the right sensors, logic solvers, and valves. Now, obviously, this is something a prerogative of instrumentation, guys. So, but however, we as process safety or process engineers need to know that the total response time for each of the sensors, logic solvers, and valves is within our process safety time. And this input can be sought from the instrumentation, and they may seek it from the vendors. So, essentially, the cumulative total of all that should be less than the process safety time, right? And so that they help engineers in guiding the right sensors or selecting right sensors. Many times the sensor, there could be a different area of sensors which is with the different response time, like your level gauges or you have guided wave radars. So these would have different times. So that in that case you look at it with this aspect with regards to process safety time. Similarly for logic solvers, PLCs are supposed to have higher fast rate than your delta V systems. So in those cases also it is a benefit where you select. Plus walls, obviously you would have on-off walls, and you know the differentiation between an on-off wall and an ESD wall or a what you call fire-rated ESD wall. They have their faster response. They are rated for different pressures and torques, and plus they are they can resist to fire to a certain limit. So those things you can select better when you know these PST or process safety time or the SIS time. Next, they help guarantee that the risk remains alarmed. Yes. So once you have this taken care of, you can be rest assured your risk is in the alarm region as low as reasonably practicable. Now, if the safe time exceeds the safety time, the protection will fail or may fail even if there is a correct SIL level. No, it is process safety time. Sorry, what was I forgot? I couldn't read the question. But process safety time is not like it is based on your like total response, as we showed you, right? It is total sensing final element and all those total encapsulation of the full graph will give you a process safety time, right from year up to year. So this is known from chemistry of your process. Huh? That's a good question actually. That brings up another topic. Like just last 4 months back, we did a HAZOP and LOPA for a company which actually produces hydrogen for cyanide. Okay, so hydrogen cyanide is the same gas which was methyl isocyanide. That was like our Bhopal gas tragedy. So their chemistry department was meticulously calculating the response or any runaway reaction that would go from this time, this operating envelope to this time, because they want to prevent any release of the PSP also, because even a PSP release is catastrophic in case of hydrogen cyanide or any of those chemicals which could be hazardous in nature, like an H2S release or a chlorine release or ammonia release. So in such case, they have to meticulously calculate this time based on your process chemistry. And that is a good question somebody dropped in the chat. So this is defined by a process chemistry, and they are the ones, or their process will define this time. Correct. Depends upon the industry and chemicals handled. Yeah, you basically process chemistry defines it in a better way. Next is a well-defined hazard. Yeah, it is about reacting for. Yeah, okay. So if shift time exceeds PST, then the protection may fail even if there's a correct seal level. Next is a well-designed SIP is not only about a seal level; it is about reacting fast enough to prevent an hazard. That is what I've been emphasizing. And then understanding and validating these times is essential for the robust process safety design. Correct. So this is basically for a robust system. Like even if there are multiple SIFs, it is important that each SIF levels credit you can take, or each SIS system as a different. There are instances where one event is prevented by several SIS. So each SIS, at what level it comes and what level it prevents that event, or what is the process, that will define the robustness of this SIFT, even if they are staggered setup or staggered set points. Okay. Next is time at risk. Now, this time at risk takes the factor takes into account the time that the actual hazardous event can per year. Examples: anti-operating, load or unloading events, batch process, shutdown process, or turn down. The initiating cause likelihood adjusted to reflect the fraction of time the hazard is prevent. So this is something which is to be read in conjunction with the enabling event. Somebody had asked in the chat that enabling event, give an example. So this time at risk is essentially a complement of the enabling event. See, if you see that many a times when you are loading or unloading, it is not a continuous process. So your time at risk is considerably reduced, and your enabling event would be something like a turn down event or a shutdown event, which essentially would not lead to that incident. So the initiating cause likelihood adjusted to reflect this. So when we do the exercise, three examples, you would see that we will be taking credit of one of these events to adjust the initiating event or take a fraction of this event. And how you take a fraction is based on how frequently is this event going to occur per year. So that is where you take a fraction of the event. So yeah, when we look at the example, I think it would make more sense there. Look at the LOPA team. So are we fine with this space, or you need any need to further slow down? Is that fine? Shall we proceed with the same pace, or anything else you want to go back? I can assure you most of the things, if you have any doubts, will be solved during the exercise, which we are going to have in few more slides. Or if there is something very important that you guys have missed, or you want me to fill up again, we can go back to a couple of slides, because I want you guys as good designers. See, our objective is not just to design a system for a client or for our EPC or something. It should be such that we are looking at the noble cause of it. Okay, when we are doing this free trainings, it is not that we are looking at any aspects of just providing knowledge. It is to ensure that you look at the bigger picture, where you design systems that are inherently safe. They don't create any catastrophe that would impact people or local community or local public who have not subscribed for that. Like the Bhopal Gas tragedy, people would have never subscribed for that. It is so many years on there, in 4 generations, for the four generations, they are feeling the impact of it. So that is something which we, as it is our responsibility, because see, not just as engineers, we are take this responsibility that we are looking. Although we are manufacturing things for simplification, better benefit of our lives, we are looking at also safer systems, safer designs. Many times I have had arguments in ASOPs, where the emphasis from the projects, or this is on mostly the schedule and the cost, but there are, like, I think many on this team are who were part of the sessions which I was involved in. I was out chairing in. We have had rampant discussions with the management, including the MDs and others, where we have emphasized that this exercise is not just for some kind of a milestone to get regulatory approvals, or just to do something because we have to give a IFC pack, or something because we have to start a construction, or something because we have to start commissioning or keep operating. The holistic objective of this exercise should be that nobody, whether the people who have subscribed for this risk or the people who have not subscribed for this risk, nobody should be impacted. It should not just life fatality. It should not be even minor injuries. You never know. Injuries today could be like if you have some lung fibrosis due to some of this. It could be not an immediate effect, but something down the line. So that is those things we have to ensure that we don't, or we do design systems that take care of such holistic safety or incidents or issues. So that is the whole objective. So I would request you guys, as maybe you would have been doing this earlier as well, but at least from today, you pledge yourself that wherever It is you as an engineer have been given the responsibility and you have the authority to take as a stop work authority. Many a times in manufacturing there's a stop work authority. So you have to call the bluff or you have to call the design wherever you see it that this is the point where this should not go any further. Don't try to what do you call impress your bosses or your management just by saying that no okay or obliging to their request. I've had HSOPs where we have gone literally at lengths fighting, discussing that, arguing and fighting that this is not what is the objective. And many a times, like those who have been with me, I have told managements or MDs or anybody bluntly, even VPs, that I'm not here or we as safety engineers are not here to do what is asked out of us by the management or the project or anything. We are here to do what is required out of us. And what is required out of us is inherent safety of a system. So invariably, whatever pressure you guys are experiences, don't succumb to that. Today, if something you succumb to, and if there's an event in the near future or any time, you will be held responsible. There are many instances where the designer is held responsible. It may not be the chairman. Sometimes there are chairmen are also held responsible for safety reviews studies, but you will be held responsible in the future. Forget about the aspects of criminal, proceedings and other things, but your conscience will also be intimidating you at all point. If you become a reason for such incidents. So I would sincerely request, don't succumb to any pressure. Do things which are right. Do things what is required out of you. Yeah, many a times doctors take oath, Hippocratic oath. They fail to it, but many a times they take it and they. So similarly, we need to comply or oblige to such safety inherent designs. Yeah. So now let's look at the LOPA team composition. Again, it's a LOPA chairman, LOPA scribe, process engineer, lead SME, instrumentation and control and power engineer. The instrument engineer is very important again for such centric. Like when in the other case in the hands-off we said the instrumentation can be non-continuous or on and off. But in LOPA sessions, it is mandatory to have the LOPA instrumentation guy full time on the forum or on the call. And then the power engineer, when they say power engineer, it is usually power backup to the instrumentations. So that is important. Next is operations implemented. As I told you, operations is our end client. So they should have operations on call. Without an operations, you can actually call off any HAZOP or LOPA sessions. We have done that. And then we have had to have somebody on call or online to fulfill the requirements. Next is process safety specialist. Obviously, it is good to have a client process safety specialist because when you consider certain aspects, they may deviate because you are obliging to the or you complying with the international standards, but those standards or those requirements may change. Like I'll give you an example with regards to BP. Now you all guys must have designed PSVs, okay? So PSV for fire case accumulation, invariably everybody in the industry considers 21% as accumulation, okay? And that is where you set your PSV and other things. However, of the many clients I've worked with, most of them Exxon, Shell, they consider 21%. However, BP is one such client that they insist that they want even for fire case, their accumulation or this to be at 10%, which is like for all conventional cases you consider 10%, but for fire in many cases you consider 21%, all clients. But BP is one such client, they insist that they want a conservative design and they would like that to be set at 10%, the accumulation. Now that is very specific to a client. So that is why I insist that you need to have a process safety specialist of the client or the EPC to be part of the forum, whereby you as going ahead with generic standards, but that may be not sufficing their conservative approach. So essentially, it is good to have a process safety specialist from the client side on call for a HAZOP as well as a LOPA. Next is functional safety expert. Yeah, I agree. BP has, the funny part in BP when I work, there is other things like many of their things are very conservatively and a different approach is done. In spite of that, there are events like the Macando one in Gulf of Mexico, but invariably their approach is very conservative. The other one is when you have a control wall stuck open scenario. Okay, I'm just giving an example because it is interesting to know. When we design a CV failure scenario for a PSV, when you say control wall stuck open, you calculate the CV and the throughput through the control wall full open CV, and we say that itself is higher. That itself is many times higher than the throughput of the plant. Your CV, whatever flow rate you are getting to the control wall for full open CV, is many times higher than the net throughput of a plant. So that is many times many clients consider that CV full open CV value as driver for sizing of the PSV. However, in PP case, I have realized that they want the total throughput through that control loop to be the sum of the main control wall as well as the bypass control wall. Because their argument is that many a times the operator may have left that bypass wall open itself, which would be unrealized. That is an unrealized error because by no means they would know that. So that is why they insist that the cumulative flow that through the main control wall and the bypass wall should be considered for PSV sizing, which many argue is an over conservative design and an overkill. But yes, that is how BP has been doing it, and I really appreciate their conservative aspects of it. So incidents happening left aside, that is different. Not just for gas blow by case, even for PSV sizing. Gas flow by case, yes, when you are looking at the rupture of the downstream system, yes, that there also they consider. But even for normal PSV sizing, where it is the what you call, CBO full open scenario, for calculating that also they consider both the bypass wall also. Next. Okay, now we look at LOPA overview. So just to give you a brief where this LOPA has come around, and yes, control wall failure scenario case, stuck open control walls. Okay, next is technique. The technique was developed by chemical process CPI industries in the late 1980s and 1990s. Then flow gas control system to prevent, maybe there as well. Okay, next, LOPA is a semi-quantitative process hazard analysis tool. Now, this when they use the word semi-quantitative, it's a very diplomatic term, and the reason they use it because it is a bridge between or a middle ground between a qualitative process hazard analysis, such as an HAZOP or a HERA, where you look at the qualitative aspects of it, and a resource intensive and an expensive quantitative risk assessment, where you look at the quantitative aspect of it. So now we can understand the difference. You know, the whole HAZOP is a qualitative study, QRA is a quantitative study, and many a times it is difficult to bridge the gap between these two quantitative and qualitative study, which is achieved through a semi-qualitative study, that is your LOPA. So essentially, that is acting as a bridge where you are looking at the qualitative aspects as well as the quantitative aspects of any incident occurrence. Okay, so that is why LOPA is of significance, and that is why they say it is a semi-qualitative and semi-quantitative analysis. Next, LOPA analyzes an identified hazard event and uses a simple set of rules to evaluate it. So that is how I will show you that. Many a times you would have read it in this that this is very difficult. LOPA is this, SIL determination is difficult, is that. However, if you segregate it to simple three steps, I think then it is very easy. Okay, QRA is quantitative risk assessment. Like you have your physical effect modeling, your consequence modeling, your what you call dispersion analysis. All of them, they are part of the quantitative risk assessment. Again, quantitative risk assessment, as they say, is an intensive and expensive quantitative, because intensive in the sense you look at different failures at different locations in a plant and what catastrophic event based on their maximum inventory, what impact it will have in the plant or if these gases escape to the community. So there they look at it with a different view. There are different softwares, DNV, FAST, Safety, you have Shelfred, you have what you call Flax and ANSYS for 3D modeling, CFD analysis. So there are different set of software. So those softwares are also exorbitant, and so that is why they are saying expensive quantitative pricing. Whereas their exercise is also expensive because many a times the client comes back with sensitivity analysis to be done for these such studies. You know, sensitivity in the sense what happens if it fails at this point, what happens at this. So there were different. So it is very like our HAZOPs and LOPA can be completed in 2 weeks for the same quantum of work. This QRA would go on for six months. So that is why it is saying expensive and extensive exercise. Okay, next is LOPA analyzes and identified hazard events and uses a simple set of rules. Okay, so these are the 4 set of rules which we basically look in the LOPA. First is the initiating cause likelihood. That means the initiation, like what is the cause that is happening and how frequently is that happening. That is your initiating cause likelihood. Then evaluates its consequences. Based on this frequency or frequently occurring cause, what is its consequences, which probably you already evaluated in a HAZOP. Next, provide layers of protection against the, so you have already provided safeguards in the HAZOP, but here, if those safeguards are not adequate, or these are not, or whatever safeguards you provided, you provide additional protection if required, or you look at the integrity level of those safeguards you provided in HAZOP. So provide layers of protection against an estimation of risk. So you know an estimation of risk, which is your basically TMEL as per that table we saw from OSHA. So that is your estimate of risk. That is a maximum risk which you need to confine your incidents below that risk. So that is the C point. And next is make improvements to the existing layers in terms of PFD average. So now either you provide additional layers in the C case, or whatever layers you provided, you provide them additional layers or additional integrity levels to ensure that their PFD average or probability of failure or demand is lower. So that is how these are the 4 simple steps of low pass. So don't complicate with yourself. Obviously, this presentation will be readily available in the I think HSC RMS website as well as on YouTube for your anytime reference or cross reference. Simple. Remember that these 4 points is how our approach is. Like for hazardous area classification, you have 6 to 7 points. You simplify that to 7 points, and you have done your hazardous area classification exercise. Similarly, for LOPA, you limit yourself to these 4 points, and any LOPA, anything you should be able, or LOPA still determination, you should be able to do in the future. Okay? Fine. Am I going at the right pace? Any other concerns here? Okay, we will do this bow tie and then we will break for lunch, because then the other part is or has to be read in conjunction with the LOPA exercise. Now, many of you would have heard about bow ties, okay? However, they are in this example, these bow ties have been very well amalgamated with the LOPA process. So that is why I wanted to take this example, because I wanted you guys to understand. If you know LOPA or if you know bow tie, I don't know how far you guys are exposed to bow ties. A bow ties is a typical study, mostly done with Shell joint ventures, and of late many of them are doing it, which looks at 2 aspects of an incident. Like, see, here you will see, I'll first explain you this as a bow tie diagram, and then we will look at it as a LOPA benefit diagram, okay? So don't go reading on this, because this is more in relation to a LOPA diagram. However, I'll explain you with an bow tie diagram. So for a bow tie, imagine that there are 3 independent incidents or initiating events, okay? These are initiating events. Now these, based on different controls, like you have designed a very well perfected system. But like whenever they say bow tie, they refer to a Swiss cheese model. I don't know how far you guys. The Swiss cheese model is typically. Let me show that. I have not. I didn't think it necessary, but let me see if I can get it on Swiss cheese model. Okay. Yeah, sure. This is the Swiss cheese model. So if you see in this, the reason I'm asking or showing you this is, see, in a Swiss cheese model, not necessarily every cheese slice would be stacked such that each hole will be aligned. The different holes would be differently placed on a slice of cheese. However, at some time it can so happen
sorry
that
to interrupt you, sir, but still we are seeing your presentation slide. You have to share.
Oh, one second.
Through the share button, yeah.
No problem. But I want to bring this up. Let's see. 1 second. Where do I have to go? Share. Shalini, I can share this directly, right?
Yeah, no issue.
I think at one point I didn't realize that this entire screen. Okay. Why am I not able to show? Okay, let me just drop this in the chat box. I think that is easy.
Yes,
that will make life easier.
Also
yeah.
fine.
Yeah, I will just snip it and drop it in this chat box. Okay. So where are we? Chat. Yeah. Okay. So are you able to, maybe you guys would refer to your this. Are you guys able to see that in the chat? Yes? There's a Swiss cheese model I've just shared in the chat. Yeah, you'll have to refer to your chat. It has gone up. Anyway, so if you look at this, see, there are different slices of cheese. Okay, Swiss, or basically they're calling it Swiss cheese just for some royalty. But if you look at this, see, there are cheese slices, each of them with multiple holes spread out across the slice. So if you want to pass something from one hole to the end, from one end to the other, from the left to right, it is not possible to do it unless all these holes are aligned. And it can so happen that in spite of all the safeguards, and now we are trying to correlate by this back to our model. So that is the whole basis of our bow tie. In spite of all the safeguards you have in the system, there can still be possible that all the holes of the cheese would be aligned in such a way that there could still be an event. Okay, so these are basically your process control. Are you able to see my PPT again?
Yes, sir. PPT is.
Yeah, PPT. Okay. So now if you see that one, like let's consider the initiating event IEA or any first event. So in that event, you have your basic process control system. Then you have an operator response. You have a safety instrumented system, and you have the self-acting mechanical devices, which your PSV or rupture disk. Now, in spite of all these safeguards already provided in the system, there could be a possibility that all of them, there could be all of these holes aligned, like a Swiss cheese model where the holes are aligned. There can be certain error or ambiguities where these things could be aligned and still lead to an event. Okay, so all these protection layers that are to the, if you see the top event which is in red, so all these which are there to your left are called as protection layers because they are preventing an incident from happening. In spite of that, there are still events in the industry and there are still events in our daily life in spite of safeguards or precautions we take. So that is how, with all these safeguards, in an unfortunate event that the holes of a Swiss cheese are aligned, there could still be an event, and that is what is our top event. So this is our top event, which is in maneuvers or overcoming of these protection layers. Now, for this event to be contained or its impact to be limited, we have these mitigation safeguards. Like I told you, we have the overflow line, we have a dike or a bunt towards a tank, or no, that's what I'll this is my question. Whatever Twitter chat, that is will be my meet question in the for the forum. So that are a mitigating event. Okay, so basically this is what gives you a shape of a bow. The bow you put on your collar, right? I'm putting a tie, but when you put a bow, this is what you get. You have your central part of the bow and you have your two flaps. One is your preventive safeguards, in spite of which an incident can occur, and then you have a mitigative safeguards. Now these mitigative safeguards are many a times in LOPA they may not consider this as a safeguard or this, but again it is subjective, so this depends upon different aspects of it. But what is more important here is that mitigative safeguards are to your right, and this forms the bow. Now the correlation with the LOPA is that all these conditional modifiers, they can limit the impact of the incident, which, as we said, right, when we discussed conditional modifiers, they said they come after an initiating event, and these tend to minimize or lower the risk of the incident. Like we said, conditional modifiers, which could be a batch process or a turn down operation. So all different things, or the possibility of occupancy or ignition or explosion. These are the things or the conditional modifiers that modify the actual condition of an event to reduce the risk. So that is how you get an hazardous event that is of lesser magnitude than which should have been. So that is why these are the conditions. So this is how this LOPA is integrated into this bow tie. So bow tie as such is looking at the protective and the mitigative layers, in spite of which there's an incident, and then you have mitigative layers, and then you have this LOPA, which is being tailored into this bow tie, and then you have the next slide, which gives you the benefits. Please explain again. Okay, we'll go again, but with regards to this description, we will go back and forth on this so that you guys understand. Okay, so see, there may be a number of initiating events that can lead to a single event. The top event usually is loss of containment. So there are going to be multiple events that could be, leading to be initiating events. There may be a number of initiating. There could be multiple initiating events. The ones which you saw on your left. Okay, I just need to recharge my, or we can go ahead for a few minutes. Yeah, so there would be multiple initiating events to the left. Brightness. Brightness. Okay. So yeah, if you look at, see, there are multiple initiating events in the previous slide, which is to your left. See, these are different independent events that can all lead to a top event. You see here, each independent initiating event. Agreed. We'll discuss this later because this is a question. So do you see mitigative initiating events are multiple initiating events. They have their own set of controls, own set of safeguards, own set of acting device, in spite of which they can lead to a top event. Okay, so that is what is said, can lead to a top event in spite of having multiple initiating events and safeguards. Next, the barriers on the left side of the bow tie are considered as preventive. That is, they can prevent the initiating event from progressing to the point of the event. So these events, these initiating events could be prevented by all these protective safeguards you are going to consider, or you have considered in a HAZOP or a LOPA. So they can prevent it. Okay. And however, in spite of that, there is an event because of the Swiss cheese model as considered. Next, barriers on the right side of the quota is considered as mitigative, and they can either prevent the event from escalating or reduce the consequence of the top event. So that is what we're trying to say. They can prevent the event from escalating to further major, like if there's a fire in a tank and if it is confined to the tank dike, so that will prevent your full tank from catching fire. So that is a worst major catastrophic event. So that can be prevented by having these mitigative. Next, in the unfortunate event that the loss of containment has occurred, it can develop into a number of hazardous events depending upon the conditional modifiers like personal occupancy, probability of ignition, or explosion as per ADLHA. So that is what we are saying. In spite of all these protection safeguards, there could still be certain scenarios or certain events which can still occur as a top event, whereby you provide adequate mitigative safeguards, and then their impact is what is evaluated or reduced based on these conditional modifiers. Okay. Next, accordingly, multiple hazard events are possible. So that hazard events, again, there could be multiple hazard events. It could only be a release of a gas, or it could be an explosive mixture that is formed, or it could be, a fireball or a fire rain, or it could be this gas release which is formed that is causing, like an ammonia release, causing asphyxiation to the downstream community. So that different, based on the conditional modifiers, that ammonia leak may not lead to ignition because it is not within the explosive range, but it can definitely lead to asphyxiation or hallucination. So that those different events are based on the conditional modifiers. Fine, I think that explains the bow tie part of it. Correct? Okay, so as I'm emphasizing, there is no finite answer for this. Many people are inclined to consider them. I will tell you the reasoning why. And many are not inclined to consider them as protective layers. But if you go with the definitions of independent protective layer, then if it fits the independent protective layer, many consider that as we'll look at that in the following slides, the definitions of an independent protective layer. So some clients consider them as an protective safeguards if it is based on if it fulfills all the definitions of an independent protective layer. However, what I have realized during my these years of LOPA review is that it is not just based on the finite or standards or codes or whether client requirements. It is predominantly based on how the systems have been configured. Like I will give you an example, very nice example. Maybe you guys would have realized, or you would realize this down the line, more reviews or experience. See, you have a typical system that you are receiving some hydrocarbon from one tank to another tank through a pump, and you have basically fire and gas around this tank, second tank, fire and gas detectors, and you have an inlet wall, automated ESD wall to the tank. Okay, just visualize this. It is a simple set. If you want, I can draw it, but it is a simple setup. So now now I have seen several clients who do not exploit the main benefits of a fire and gas detection system. Like they would predominantly configure a fire and gas detection system only to provide audio and visual hooters and alarms, okay, audiovisual hooters at the local site and alarms in the DCS or PLC room. So what they are doing is they are just using this mitigative safeguard, which is the fire and gas detection, to only alert the operator or people in the vicinity or the community to evacuate or and go to the assembly point. In such cases, I would personally not consider that recovery barrier or that mitigative safeguard as an example for low power, because it is only an alarm and notification system. And although it is because of, suppose there is a spillover from the second tank and there is containment in the dike, so there will be some gas in detection. It is, but it is not really doing the benefit of any protection layer. However, consider the same setup, same two tanks, between a pump in between, an ESD at the inlet of the second tank, and a fire and gas detection system with another client, okay, who has designed a system to be very conservative or impeccable with high integrity and good system. So what he would have done is he can use the same fire and gas detection symbol to essentially isolate the tank or isolate the second tank by closing the ESD valve, because you don't want to fuel or add fuel to a fire scenario. So that is conventional design, or it should be. That is how it is a good design practice. So he can either automate the inlet ESD valve to shut based on fire and gas detection, or he can also use that same fire and gas detection signal to trip the supply pump. In both these instances, this IPL or this barrier or this fire and gas detection system, which is essentially a mitigative barrier, can be used as a protection layer because it is cutting off the hydrocarbon supply to the fire. So it is not adding fuel to the fire, although this incident has happened, but it is not exflagrating the incident by increasing the quantum of inventory or hydrocarbons adding to that system. So essentially, in this scenario with the second client where he has configured it to cut off the supply of hydrocarbons either through the ESD wall or through the pump or by tripping the pump, we should be considering that as a credible protection layer. Does that answer your concern? I think it's a tricky one, but this is based on how the client has specifications and how he has configured the system. Okay? Fine. Any concerns on that? Because that's a like this deliberately I kept this slide or this question because I wanted to understand the pulse of whatever we've discussed. I think most of them had said no, which I don't tend to differ with their opinion. They are right in their own place, but there are instances where based on this typical configuration and client specifications, they have been considered as credible protective layers as long as they meet the requirements or the criteria we will be discussing in the next future slide. Yeah, that is a practical explanation I gave and practical example. And then many a times in like just the last week, a couple of months back, we did for Stanlow Refinery. They had not configured their system or their fire and gas detection to trip any of the inventory or any of the supply lines. So basically, we provided that as a safeguarding. You can see, I think, in one of the actions or case studies we'll be studying, we insisted that they use that as a tripping point and that tripping safeguard, and then that was considered as an adequate protection layer. And then basically we were able to demonstrate alarm. Otherwise, without that, we were actually going in SIL 4 region, which would have required full redesigning of the full facility. Okay, so that is a good example where we can demonstrate that these mitigative barriers can also be considered as protective barriers as long as they are configured to do the protective action. Okay, now with most of the team on call, I think we will proceed to the simple flow sheet for how do you conduct a LOPA. Okay. LOPA on a boiler, that is it is difficult to provide it depends upon which scenario and what it is. Right now I don't have any example for LOPA in a boiler, but maybe a couple of months down the line I will have an example because I am scheduled to do a boiler case study. So hopefully I will have that. But as of now, I don't have anything for LOPA on a boiler, example for LOPA on a boiler. But I think if you look at this flow sheet, suddenly why am I not able to navigate? Yeah, so maybe a couple of months down the line, I should have some example for LOPA on a boiler. And then, but however, if you look at the basics and fundamental approach, we should be able to target any of them. It's not a big deal, though it's you follow the same approach methodology for LOPA, and I think it should suffice to do any LOPA on any system. Okay. Yeah, so now we are at this methodology, LOPA methodology. Hope you guys are able to see the flow sheet.
Yes, sir.
Okay, great. So the first step is simple. Identify the hazard event and define the consequence. This is what we always do in a hazard. We do this in any HERA study or a HAZOP study or any PHA study. Simple. Identify the hazard event and define the consequence. Like I said, worst unmitigated consequence we need to define. Okay, or different types of consequences we have to define. Okay. Now remember, whenever for a LOPA study, it is imperative that you look at each consequence. You may have tabulated n number of consequences in the HAZOP, but in a LOPA study, look at that consequence as a single initiating event and then do the evaluation. Do not try to mix the consequence event. Like I will show you a flow sheet where the client insisted on mixing it, but the problem is that the cumulative TML values and all those things change. So the normal practice or good practice is deal with every consequence event as a individual what you call initiating event and look at it separately in a LOPA. Okay, so here you can define the consequence types different and then deal with it one by one. Okay, because not all the consequences may have the same severity, to put it simple. Okay, now once you have defined the event and consequence, then select the applicable consequence severity and its associated TML. Exactly. So this based on the severity of every consequence, which could be different, you select a TMEL for each of them. That is also the reason why you have to look at it separately. Next, identify all initiating causes which can result in the identified hazard event and quantify. So all the initiating causes which can result in the hazardous event and quantify. Again, here they are saying, they are trying to club the initiating causes all together, which we should not do. We should look at it as an independent initiating causing event. Okay. Next, identify all applicable IPLs which prevent the hazardous event from occurring. So this is what you've already done in a HAZOP. So you again document that as part of the LOPA. You identify all applicable IPLs that you've already considered or those were recommended. Next, identify all applicable conditional modifiers and quantify. Again, this is the conditional modifiers we spoke about: probability of occupancy, probability of ignition, probability of flammability, etc. Okay. Next, are there more initiating cause? Yes, if there are different initiating cause, like we said, we listed different consequences, then go back to the initiating cause, identify each initiating cause, and then evaluate it separately. Okay. If no, if there are no more initiating causes, then go to determine the intermediate frequency of the initiating cause. So intermediate frequency means basically the exercise which involves evaluation of the enabling events or the safeguards and the conditional modifiers together. I will show you that in the next slide. This is the step where you look at all the available safeguards, all the available initiating events, and their enabling events, and all those you look at it as a single entity. And once you have that value, you compare that with the total intermediate frequency level TMEL, as we discussed in the chart. For every severity, there is a corresponding TMEL as defined by OSHA. So look at that. So once you determine the qualified risk identified gap to be met, so based on this, between the calculations we have done for all the safeguards and the calculations for TMEL, if there is any gap, then you fill that gap basically by the risk reduction, either by providing a safeguard, or you are providing anything else as a layer, or you are providing a higher integrity layer. Okay, so determine the identified risk reduction gap to meet the achievable TMEL. Now, via an ALAP demonstration, determine what more can be done to ensure the level of risk is broadly acceptable. So this is basically we try to say that this is what is an event. And based on the risk ranking, are you able to further reduce this based on the safeguards or based on the integrity level? Yes, if there is more, if you are able to do that, and if there are more events, then you go back to yes to the first step. If there are no more events, you end the cycle. Now, it is just your reference how to approach our methodology. However, when we do the examples in the next slide, I think that will make things simpler and understandable. Yeah. Okay. Next, layers of protection methodology. See, again, here we are saying the intermediate event likelihood for each of the threat line is calculated by multiplying the following factors and resulting in a frequency per year. That means you have to establish that what is the frequency of that initiating event, like how frequently that can occur in a year. Once you have these three calculated, only then you compare it with the TMEL. So what is that multiplication of these three factors? One is the initiating cause likelihood, then the PFD. Yeah, conditional modifiers we discussed, I think, during the definition time. You were not there, but okay. We will look at these conditional modifiers again when we are in the calculation sheet. Next is PFD average of applicable protection or mitigation layers. See, if you see here, they are saying protection and mitigation layers. They are considering mitigation layer also. This client did insist on mitigation layers to be considered also. And then looking at these conditional modifiers. So you have to have one entity that is a multiplication of all these three things: initiating cause likelihood, PFD average of applicable protection, and conditional modifiers. Okay, and then the IEL is then compared with the TMEL. The TMEL was where we looked at it in the table. You know, when we look at this exercise, we'll really go back there, where we said TMEL for severity 3 is 10 raised to minus 3, for severity 4 is 10 raised to minus 5, for severity 5 is 10 raised to minus 6. So that chart. So now this, if IEL exceeds the TMEL, if this value of IEL, this multiplication of this exceeds TMEL, then additional reduction is required. Simple. Okay. Then based on the additional reduction, an alarm demonstration should be performed based on whatever reduction you considered, and any additional protection identified should be implemented. The most effective hierarchy of control methods should be considered. Hierarchy of controls here means first you provide a first if you already have a safeguard or in the system, then you look at increasing its integrity so that you are able to meet the alarm. If you are not able to do with that, you provide an additional safeguard. Now, whether that additional safeguard is getting you the risk reduction of whatever 10, 100 required, that is important. If it is not, then you again increase the integrity. And then third, you also look at possibility that if all of these are not doable, then you look at an inherent safer design, whereby you look at higher design parameters or measures which can reduce the risk. This is usually done when the SIL is going to a much higher level of more than 3. Okay. If the IEL figures cannot be reduced below the maximum frequency criteria by inherent safer design measures, then outstanding risk reduction measures is used to define the integrity requirements of the SIF using the SIL tables discussed above. So this means that if the IELs cannot be reduced to below a certain frequency by inherent safer design, then the outstanding risk reduction is used to define the integrity. That means if you are not able to do things with inherent safer design at the onset, then you provide the inherent or increase the integrity, either add safeguards or increase the integrity of the existing safeguards. And if even that is not done and it is crossing SIL 3 and above, then the management director will straight away do for a redesign where you consider inherently safer safeguards. Okay, so that is where I don't consider SIL 4. So next is a step. Okay, again, let us look at these are then now we'll be looking at 3 industry examples. Okay, of actual LOPA analysis conducted for UK client. This was done a couple of months back. So we look here in 3 possibilities. One is that initiating event frequency is less than the TMEL, whereas where the system is considered inherently safe. Okay, next the IEL, which is initiating event likelihood, is equal to the TMEL, where the system is safe, no additional safeguards are required here. And the third and the most severe one is where the IEL crosses the TMEL, whereby you need additional safeguards, you need risk reduction or higher SIL required. Okay, so either of these 3 approaches has to be taken if this IEF is greater than TMEL. Fine. So let's go to these 3 examples. Now I will have to share this work. For whatever reason, I am not able to share this too. Shalini?
Yes, sir.
Over again.
Hello.
Are you able to see Excel file on my this?
Yes. Yes.
Yeah, everybody, right?
Yes.
Okay. Okay. Not able to. So can you just refresh? I've just shared it now.
I think. Yeah, I think it's showing now.
Yeah, many are saying yes. Some are saying no. Oh, it's an Excel file. Excel file. Those who cannot see, can you please log in and refresh, because half of them are saying they can see it. Okay, now are you able to see a PDF PNID?
Yes, sir. PNID is also visible, sir, on the screen.
Great. Okay, so I think all of them can see in a PNID and the Excel file. So yeah, this is basically the PNID which we did of a startup heater. Basically, this was a carbon capture project, and this is basically flue gas which is coming from refinery exhaust or whatever, and this flue gas is going for carbon capture, basically the acid pretreatment and other things. So I have confined this only to this PNID, so that downstream is a pretreatment reactor or carbon capture reactor, and this is a preheater whereby you heat the flue gas to its prerequisite temperature required for the reactor, and that is done through two sources of fuel. One is ammonia, right? This is ammonia, is it? And the other is fuel oil. Fuel. 1 second. Yeah. So one fuel source is fuel gas or fuel gas. Okay. And the other source is propane fuel gas. And this one is hot air from the air header. Okay. So what they are doing is basically this is the flue gas which is passing to the downstream system. They are taking a slipstream of from this flue gas and passing it to the startup heater, which is heated by propane and fuel gas. Okay, so this is your startup heater. This is more or less what it is, and then this slipstream, after heating, it combines with the main flue gas stream and provides the prerequisite temperature required for your downstream reactor. Okay, so this is our PNID or the system, and our all three scenarios which we spoke with IES, equivalent or greater than, smaller than, are in this same PNID. So if you guys are able or absorb the PNID, let's go to the worksheet. Okay. Okay. So this first case is where you have, yeah, there is no gap here. Okay. So see, this was a scenario where you have this FV24 FV101 stuck open and more flow in the hot air line 2 during to startup heater during startup or initial heat up. So as you would see in the PNID, this is that line FV. Yeah. So this is that control wall FV101. Okay. See FV101. Okay. Then this wall is considered stuck open, and the contemplating scenario is that if this is stuck open, then there is more flow of hot air to this startup heater. Okay, because of the CV of the wall. In which case, probably there would be a flame off scenario. Let's look at what the consequences would be. Okay, so possible flame blow off, okay, in the startup heater, leading to uncombusted fuel gas and air mixture passed on to the downstream system, like reactor, or these are the three reactors, where it can be combusted on source of ignition. So that was a scenario. If you look at it in the PNID, again, I'll go back just for the explanation. So if this control valve sticks open, When I say stick open means that could be due to any reason. Okay, it could be failure of the what do you call supply, failure of instrument air supply, or failure of power, or failure of IO signals, or anything. My usual approach is I always consider it as not fail open or close open or all this. I say stuck open or stuck close, because that covers all the scenario, whether it is failure due to instrument air, failure due to power, failure due to IO instrument inlet outlet lines, anything. So okay, so that scenario it is fail open, stuck open. Sorry, it is stuck open. In which case, remember this is a fail close wall, but the actuator can stick open, right? So once it sticks open, that may pass full CV of or gas equivalent to full CV of this control wall into your downstream system. So once that happens, is basically in your air, startup heater, there is a possibility that this air will blow off the flame, because the flame will not be able to sustain when such high flow rate of hot air is witnessed. Okay, because it is done built for some stoichiometric ratio. So once this happens, this combustion air can actually blow it off. Okay, so that is how we have arrived at this scenario where we say possible flame blow of the startup heater leading to uncombusted fuel gas. Now, once that flame blows off, obviously there is either propane or there is fuel gas, plus there is air. So now that is a very highly combustible mixture. Okay, and then this mixture is, because of this hot air or because of this air, is propagated to the downstream system, which is the set of three reactors in this case. Okay, so that is how we are contemplating this scenario. And once it leads to combustion, if there is a source of ignition or combustion, that can lead to explosion or deflagration inside the reactors. So that is how our scenario has come up. Okay. Any doubts on this? This is the start. You have to understand the scenario. This is mostly come out of an HAZOP. Okay, and then we will look at the LOPA part of it. Any clarifications or anything here? Okay. Now, if you guys have understood this part of the system design, then let's look at the HAZOP or HAZOP part we have discussed. HAZOP is already documented. We'll look at the LOPA aspect of it. So now you see, this is the scenario, stuck open of this valve. Now, based on this FV stuck open as part of control loop failure. Now, what is, the client has provided certain definitions, okay? So what they are saying is, for a control valve or a control loop failure, if you look at this, see, these are the initiating events, okay? Somebody was asking me, give me an example for enabling or initiating events, okay? So this is the initiating event. First of all, if there's no initiating event at all, you just put it as 0. If it is an initiating event that is due to a control system failure, you consider it as 0.2. If it is a pump failure or an initiating event due to a pump failure, you consider it as 0.1. If this event is due to a routine task error, means an exercise which you are doing routinely, like once in 2 months, once in 3 months, maybe part shutdown, plant shutdown, or even as a maintenance activity, then you consider it as a routine task error. And then the other one is occasional task error, means if you are doing some exercise, like if you are having some functionality testing or performance testing of something, so that is an occasional exercise, so which we can consider it as lesser frequently occurring, because it is once in a year or once in 2 years. So in that case, you consider it as the 0.1. Now there are certain events which are rare task errors. Maybe like on a PSP, you do cold differential testing after a certain time, or you do performance testing or auditability testing, or any kind of testing which you are there. So that is once in maybe 2 years or once in 5 years, which is an unfrequent event or infrequent event. In those cases, you consider it as a rare task with a lesser probability of initiating as 0.01. So these are well defined. For our FV control valve stuck open, that is a control system failure, which corresponds to 0.2. And the same has been considered here as an FV stuck open as part of the control loop failure as 0.02. Okay. Now, this is part where you are giving initiating event, or you are giving constraints or restrictions to an initiating event, like an enabling event. This is an enabling event where it is happening, or this control loop failure corresponds to 0.2. Now, the other thing that is supporting this enabling event or this initiating event is an startup event. Okay, now this is only happening during startup, because you are what is startup heater, the name itself says that only during startup, to meet certain temperature, okay, or heat of this for a stoichiometry, you are heating up that flue gas. So this activity is only related to a startup event and not during normal operation. Now during normal operation, this heater would have been bypassed. Okay, so essentially this event is only happening during a startup event. So that is why we have listed it as a startup event in the initiating events. Okay, and the reason for enabling, or this is part of the enabling event, because a startup is a infrequent scenario, and the frequency of startup you have considered is that this is as per client. Okay, that they have considered it as once in 4 years. So once in 4 year means they are not expecting a frequent startup, or not. This is not startup after immediate shutdown or a plant shutdown. This is something like once in 4 years, when during a plant shutdown they will be having this scenario or using the startup return. So that is why they are saying once in 4 years. So whenever we say the initiating event, it should be standardized for once a year. Okay, so when you look at it, 1 divided by 4, it is 0.25 times in a year. Agreed? Fine. So that is what value we have provided as the conditional modifier also. If you look at it as a startup event after plant shutdown, considered at once in 4 years against the time at risk. So here the time at risk for anybody operator who would be there in the vicinity. Usually during startup, see they are saying during startup at least one operator is available in the vicinity. So during startup, which is an event that would happen once in 4 years, okay, with a fractional exposure or time at risk of 0.25 years, we are considering that this operator will be exposed to this event. However, that frequency is 0.25 times. Okay. So this is what we have given as an initiating event. One is this part of the control loop failure, and the second is this one. Now, the next part is the independent protection layers. Okay. So here, as you would see, these are independent protection. These are conditional modifiers. We will come to the conditional modifiers later. So now we have to look at independent protection layers. So first is, if you see here, there is a specific, like this has come out from the HAZOP. We have taken credit of this in the HAZOP. So this is the first layer, which is an alarm and operator action. So what is the first layer? Or they have mentioned it as IPL 1, 2, 3, 4, 5, 6, whatever n number. Okay. So here what they are saying, configured hand switch to shut down the burner when no flame witnessed by operator. That means there is a side glass or something of a device which shows that there's a continuous flame. If the flame is not there, then the operator, based on his visualization, he can go and switch off the burner. Okay, to shut down the burner when no flame is witnessed. To show you in the PNID, see, this is that no flame. You see here, flame on, flame on. Okay, so these are indications that the flame were on, and this is required when you are starting up the, or this is required to be on when the heater, this heater is functional during startup. So once there is no flame, that means the operator can see that and he can go and directly shut off the burner. Okay, so that is your first layer of protection. Fine. Next, there is saying that flame off indication to trip the burner. Now this is an PPCL alarm. Oh, sorry, I confused you guys. This one's a hand switch. If you see the PNID, this is the hand switch, which the operator is. See, you see this 24HS518, which is the hand switch 24HS518. Okay, so this is what is going to be used first safeguard by the operator. He will use this hand switch to switch off the burner. Now, the second safeguard is this flame of indication. So based on this flame of indication, okay, this will trip the burner. This is a safeguard inside the burner itself, BPCS itself. So once there is no flame detection in this part, there's no flame detection or no flame on, it will automatically trip the burner. Okay, this is part of the burner control itself. Okay, so that is our second layer of protection. So as you see, we have considered this one. Okay, so this is based on again IPLs. These IPLs are provided by the vendor. If you look at first IPL, okay, so if it is, so here he is saying, see, BPCS, because in the first IPL we have considered that operator taking action. So we have considered BPCS or basic process control system through the operator as 0.1, and that is how we are getting 0.1 here. Okay. Similarly, for the second case, it is an automated function. Okay, it is an automated through the BPCS loop. That is why we are saying it is a BPCS alarm also. And if you see here, there's a BPCS alarm which says 0.2. So this 0.2 is coming from here. So here you have multiple. Suppose you had multiple BPCS alarms, so that can create a confusion to the DCS operator. So in that case, there is a slight lesser reduction they have considered. So typically there are different definitions for different scenarios, but for our applicability, this BPCS alarm, which was 0.2, that is where you get this value from. Okay. Now, next, the IPL 4 is provide this. We are saying this is a recommendation which came from the HZOP. However, this exercise LOPA is done after the HZOP, so we are taking credit of that safeguard from the HZOP recommendations. Okay, so here I am saying provide configure a low pressure trip. Okay, on this 504, 505, 506 to shut the burner during flame out scenario. Okay, if you see here in the PNID, see they have considered a temperature transmitter, and that is 2 out of 3. Okay, 2 out of 3 voting. Hope you guys are aware of 2 out of 3 voting. So here that means it is already, see, you see these are 3 transmitters. 2 out of these 3 voting means as long as there is confirmed low temperature, here they have given high, but my recommendation is for low. When you say flame out, that means the flame is not there, so the temperature will go to low conditions. So when there are 3 detectors, 3 transmitters, and out of that, if 2 are indicating low, that means there's confirmed low temperature. In that case, it should trip the burner. That is my recommendation from the HZOP. Okay. However, you see there is already a SIL 3 loop provided in the PNID. You see the pressure transmitters are already in SIL 3 configuration. Okay, here it is clearly saying 2 out of 3. That means there are 3 independent pressure transmitters. Okay, of SIL 3 rating. These are already provided SIL 3 rating because of the burner criticality. So that is what they are saying. But what, as a vice designer or as a vice chairman, I am suggesting that you don't put anything additional in the system. You already have an infrastructure for 3 transmitters. You utilize the same to just have alarms. So these alarms are not additional cost. So just put alarms here, and based on these alarms, you configure. The system is already configured, but you take this input from the alarms, low temperature alarms, to configure to trip this burner. Is my recommendation from the HZOP, and I will be leveraging the same thing here as a for my LOPA. Okay. Now, since it is SIL 3, if you look, I hope they have provided SIL 3. Yeah. See, when it is SIL 3. This is what they consider 0.001, and essentially it is 10 raised to minus 3, means SIL 3 only. When you say SIL 3, even as per our definitions, it is 10 to the power of 3. Okay, SIL 3 about 1000 and 10,000. So we are just on the boundary. We are saying 1000. Okay, so that is why we have considered SIL 3 here. Fine. Anything you guys don't understand, please, we can raise an alarm now so that I will try to explain to you. If we go further into the system, you will be lost. Okay. So that is how we have this IPL 4. Next, so these are all safeguards we have to provide. We have provided the constraints or limiting enabling events of the initiating event. Then we are looking at the different safeguards that are either provided in the design or have been provided or recommended in the HZOP. Okay. And then there is something which is additional. If you see here, like obviously these are conventional safeguards. Okay, there is a hand switch which the operator can use. Then there are flame off from the BPCS, and then we are providing a trip through the burner management system. However, there is this additional things which the operations emphasized on including, because they are saying that there is excess of CO fuel gas or excess of this carbon monoxide flue gas with fuel gas, and the air mixture resulting is 1000 ppm concentration, while the propane is in 21,000 ppm. So what they are saying is that the gas, CO flue gas, basically this flue gas, which is this is the CO flue gas, okay, carbon monoxide flue gas. See, if you see here, it is flue gas from the carbon monoxide generator, I think. Boiler, sorry, from the CO boiler. So this flue gas, they are saying, is already excess flow. Okay, and even if this fuel gas and everything mixes with it, the concentration achieved here is 1000 ppm only. Okay, whereas for the fuel, either the fuel gas or the propane to be in the explosive limit, you need to have a concentration of greater than 21,000 ppm. Okay, that is what is the argument here. Fine. However, I am not taking credit of that, because the reason to that is because during a startup, it may so happen that the operator may have kept that flue gas valve closed, or you have so many spectacle blinds there in this system. You see, you have spectacle blinds here, or you even have these, like if you have upstream, there's a wall here. So because of that, I'm still not taking credit of that, because during startup it is quite possible that these walls would have been closed. Okay, so that is why this is left as 1 without taking any credit of that. Fine. Now we will look at the conditional modifiers. Okay, so in this case, conditional modifiers, basically here you have first one, which is occupancy. So during startup, only one operator is there is a sure operator available. So we cannot say that there's an operator sitting in the DCS room or something. That operator is required as per SOP to be around that startup heater to monitor the startup process. So essentially, that is the reason we have considered him as an occupancy, full-time occupancy of 1. Next, see, there is source of ignition. Yes, not from external sources, but within the systems. Yes, there could be source of ignition. Next, vulnerability basically is again of the operator or the people in the vicinity. Now, the time at risk. Again, as I said, this is a conditional modifier because this event is not happening every day, day in, day out. It is happening once in a year, only during startup, because this is a startup heater. So here I'm saying startup event after plant shutdown, considered as once in 4 years. Against time at risk means the time, if the operator is even present here, he is required to be only once in 4 years. That means 1 divided by 4 is 0.25% of the time there, not full 1% or full 100% of the time. So that time at risk is considered as a fraction of 1 by 4, which is 0.25. Fine. Hope you guys are with me. You guys are awake, right? I know this is a little cumbersome part, but it's better to understand it now. Okay, so I presume you guys are following what I'm saying. So this is what exactly we were saying in the flow in this presentation, where you have the sum of these 3 calculated. Okay. Yeah. So this is what we did. This is what we did just now. We looked at the initiating event likelihood. We looked at the PFD average of the protection layers or mitigation layers, and then we looked at conditional modifiers. So these 3 things we looked at, and that gives us our IEL, intermediate event likelihood, based on the initiating event likelihood or initiating cause likelihood or the PFD average and the conditional modifiers. Product of all these 3 is what is our intermediate event likelihood. That is what we are getting it here, intermediate event likelihood, IEA. So this is a sum or product of all these values. You see here is a product of all these values. Okay, fine till now. Okay, now we are going to have this TMEL because we need this for comparison, right? Target mitigated event likelihood. From the flow sheet, if you look at it, here is where we get the TMEL. See, this is the TMEL, okay? As if you recollect, in the morning session we discussed based on UK OSHA guidelines. So based on our severity, whatever severity we get during the HAZOP, this is the definition of each of the impact or severity, and this is the TMEL they have provided. This the OSHA has provided, okay? So in our case, I think the TMEL is 10 raised to minus 6, means this event, or if there is any combustible explosion in the reactor, that could lead to at least a single public fatality and multiple fatalities within the plant, more than 2, because a reactor explosion can lead to more than 2 fatalities. So that is why this is severity, 5, or this is this severity 5 is also from the HAZOP HAZOP worksheet risk matrix. Okay, that is how we are getting this TMEL of 10 raised to 6. I will show you this in the flow sheet. See, in the flow sheet, this is where you provide the TMEL. Okay, see here you have mentioned the consequence: multiple UK fatalities, 2 to 10 deaths, or a single public fatality. So based on this, there's 10 raised to minus 6 is what is our target. Means we have to have our initiating events or this product of all these events either lesser than or equal to 2. So in this case, if you see, this same value is coming to this 10 raised to minus 6. Okay. And based on our product calculation of all these 3 values, that is the multiplication of the initiating event, the independent protection layers, their PFD average, and the conditional modifiers, So this exactly matches this value. So that is why it is saying no gap. That means there is no gap and your design is inherently safe. Fine. So this is how, so once you give this, there is no gap. So then what is my recommendation? Is that I have already considered this recommendation in the safeguard, in the HAZOP. However, now I want to have this as, see, based on the considered SIL3 high temperature trip in the design, same infrastructure can be used to provide low temperature trip, that is low temperature, these are the transmitters, to shut the burner, which would provide adequate safeguard to the scenario. That means what you have already considered as SIL3 in your designs. In this case, the client had already considered SIL3. They are many a times proactive. Many a times they do so to avoid that going with the schedule delay, because if they go with every SIL, then it will increase the cost as well as the schedule by say 6 months. So here, because it is a burner management system that is part of a burner vendor package, so he has already considered SIL3. So that is why the conclusion is based on the same things, based on SIL3 high transmitter considered in design. Same infrastructure to be used to provide low trip. Just providing an alarm or a trip is not, there is no additional cost associated with it. Probably the soft link to the burner is the only cost, but that saves considerable cost. So in this case, essentially there was no gap, and whatever they have considered is adequate, SIL3 adequate. Only thing is they have to add an alarm, low alarm, and a low trip in the existing infrastructure. Is that clear? Maybe anything, please. This is first example. Try to understand. This is the easier example, so try to understand this. If you have missed anything, let me know. Lane operate burner that. No. If you look at this, there are three independent. See, one is this configured hand switch. Okay, that is through the flame side glass. Basically, there is a side glass here as well, which may not be seen here, but there is a flame side glass hand switch. As we were instructed, there's a side glass or some kind of indication to see here in this portion for flame witnessing. So that is one independent layer whereby the hand switch is being shut off by the operator based on the flame observation. That is the first layer. That is an operator intervention step. Second layer is flame of indication to trip the burner. Now that is your flame off. This flame of indication is basically tripping the burner through the PPCS. Now this is doing through the basic process control system, that is based on the burner management system itself, BPCS. Okay, and the third layer of protection, this is independent, which is through these temperature transmitters. It is stripping off this burner management system also. Here, if you can say, the burner management system is the final element, but essentially this PMS, they have already considered SIL3 level PMS. So when it is already high SIL integrity, we can consider this as an independent layer, because invariably it will still act as a independent loop for this safeguard. So these are three independent layers of protection in this system. Fine? Because they have considered SIL3. If it was not SIL3, then yes, then there would be certain concerns with whether they have, because say if they would have considered SIL2 also, then we would have to relook at it, okay, as a design part. But now they have, the client has, or the vendor has, the burner management vendor, based on his typical design, has considered SIL3. How IEL value, what is this? How IEL value of, what is it? One second. Where was that? How IEL value? New message. How IEL value of the PPCS layer was allocated. Okay. See, this is their, this, okay. So this is PPCL alarm. So if you look at this, what value we've considered is 0.2. Yeah, so 0.2. So this is based on their arrangement. If you see PPCS alarm, see, first is for PPCS with operator, they are considering 0.1 because there is operator intervention involved here. Although it is with the same PPCS, it is through operator intervention involved here. Whereas for this PPCS, they are saying it is through the automation based on flame detection, their monitors or sensors they have. Based on that, they are directly able to do it without an operator intervention. That is why they have considered a higher level here. Fine. Luckily, we had these client guidelines, which was well defined, and that was sufficing for all the scenarios. So that is why we were able to align or concur with these ones, and then provide the safeguards or provide the values, credit values here. Anything else? One second. Any other thing in the chat? Can you show the actions part again? You mean the actions is initiating events, right? Yeah, again, just for quick, this was basically control valve failure. This is the initiating event. If we stuck open, however, this is an startup heater which comes into picture only once in 4 years during a planned startup. So next is that because this control valve FP stuck open as part of the control loop failure, this point 2 is coming from the client definition itself, where they are saying that the initiating event is that initiating event. Okay, that an initiating event that is an outcome because of basic control failure should be considered point 2. So you will consider point 2. Next is this IPLs which are there. So we have to look at the product of all these three. Okay. Initiating event, IPLs, and the conditional modifiers. So again, the IPL here is a 0.1 because it is through an operator intervention, and that is how they have defined it through based on flame sighting. Second is flame off through a PPCL, so that is again defined as per that it is 0.2. And third one is a safeguard that is considered in the HAZOP. However, there is already SIL3 infrastructure there provided through pressure transmitters and the burner management system all rated for SIL3. So we have considered SIL3 here. And here, this we are not taking credit for because there is this flue gas is during startup. This flue gas could be at a lower flow rate. So that is the reason I'm not taking credit. Then during startup, you have this conditional order. Again, there is one operator who is required to be there for continuous supervision during startup of the heater. So that is why we considered his presence as one. However, this exercise itself happens at once in 4 years. So the time at risk is once in 4 years. That is why we consider 0.25. This gives us a product of all these three factors. Okay, and that product turns out to be exactly same as the TMEL that is required as per UK guidelines. So that is why there is no gap here. And I'm only saying that the existing infrastructure should be configured to provide low temperature trip, which should suffice for this scenario. Okay. Next, let's look at the scenario where okay, so this is a scenario where your IEL is lesser than the TMEL. So it is more or less there is no gap because this is a favorable scenario. Okay, this is in the same PNID. You have this FV103 partially closed and less flow in the fuel gas to the startup heater. Now, if you look at this PNID, FV10, yeah. So okay. So this is that control wall. You see FV103. Now, many a times it so happens that this is your package boundary. So this they are not indicating, but there is a control wall, which obviously is evident in the vendor design or whenever there is a vendor package. But these two control walls are there, okay? And this control wall, one of them is on the propane line. FV102 is on the propane line, and the second one, 103, is on the fuel gas line. Fuel gas to startup heater, okay? So now we are contemplating a scenario where it says FV103 is partially closed or less flow of fuel gas. Okay. So in this case, what is the worst that can happen if there is FV or this valve is partially or stuck closed? So in this case, there could be possible flame blow off. Okay. The reason for flame blow off here is because of unsustainable flame due to lesser fuel to air stoichiometric ratio. So you guys would have done stoichiometry in your college days, okay? So you need a certain stoichiometric ratio for a fuel or to air or air to fuel to sustain the flame. So since here the fuel gas flow is constricted or there is partial flow of fuel gas, so it is not able to maintain this fuel to air stoichiometry in the startup heater, and that could lead to uncombustible fuel gas and air mixture passed on to the downstream, because the flame is not able to sustain this due to the inefficient stoichiometric ratio. So then that flame will go off, and then there is a this fuel or partial fuel gas that will essentially be mixed with the air, because you have combustible air. So this is forming a combustible mixture, and this is again passed on to the downstream reactor, okay, where it can find a combustion, or where it can combust when there is a source of ignition. Okay, so this is typical to the earlier case, but earlier case there was more air and that was blowing off your flame. In this case, there is partial fuel gas which is not preventing the flame to sustain, and that is why there is a flame blowout. Okay, so let's look at this scenario. So in this case, we are saying this is a partially closed and less flow in the fuel gas to startup heater. Okay, again, this is part of the process control loop failure, and as per the client requirements, this is part of control loop failure and hence considered as point 2. Point 2, yeah, you consider it as point 2. Now again, this startup heater is something that is happening during a startup scenario or only during once in 4 years. So based on that, we consider as a time at risk of 0.25, which essentially can be part of the initiating event, or it is considered as time at risk here. Okay. Now let's look at the safeguards. Once we have defined these initiating events, which here you see the definition of 0.2 for the control wall, and this 0.25 as part of the conditional modifiers. So then let's look at the independent protection layers. Here also you have similar independent protection layers. We have the configure hand switch to shut down the burner when no flame is used. This is again operator intervention, and based on their nomenclature or their guidelines for operator intervention for IPL1, we have considered BPCS of 0.1. Okay. Now there is the same BPS in the 0.2, but it is through BPCS alarm, which is automated. And this BPCS is a flame alarm as an indication I showed you in the PNID. Yeah, this is the alarm, flame off, flame indication, which is going to have BPCS. And that is why we consider this as 0.2, like done in the previous instance. Okay. Now, the third safeguard, again, this was a recommendation from the HAZOP, where I said provide low temperature transporter, similar to the earlier case. And I'm taking that same safeguard here, which is SIL 3 rated. The infrastructure is SIL 3 rated, going through the burner management SIL 3 rated system. So we have considered 0.001 as a factor reduction here, risk reduction. Now, in this case, if you see excess of fuel gas with fuel gas and air mixture resulting, so here also there is the same argument that there would be excess of fuel gas. However, in the earlier case, what was happening was that our fuel gas valve, or this was continuously open, okay, and that was a blowout due to excess of carbon monoxide. In this case, what is happening is your fuel gas flow itself is constricted. So your scenario is much catastrophic from the earlier case, because your fuel gas, which is required for combustion, that itself is constricted. So the quantum of fuel gas that is not able to sustain stoichiometric burning, and that quantum of fuel gas which will be passed on to this is considerably low because of the partial or constricted flow or partial no flow. Okay, so in that case, what I'm doing is here I'm taking credit of it, because my volume of fuel gas is considerably low and it will never reach this mixture LEL concentrations. So that is why here I'm taking credit. Whereas in earlier case, if you see, I have not taken credit for this. I've kept this as 1 itself, because the fuel gas flow was at its full flow. Okay, and the reason cause for this was blow off of the flame due to the high flow of carbon monoxide or the flue gas. Whereas in this case, my fuel gas flow itself is constricted, and due to that, I can take credit of it, because there is a very small composition of this fuel gas which will be passed on to the reactor, and essentially it is not falling within that LEL range. Okay, so that is why you would see an additional 0.1 here that is not there in the previous case. Next, again, during startup, there is at least one operator required to be there, so that is part of the conditional occupancy. Okay, ignition source can be possible inside a furnace. You will have inside a reactor, you could have multiple sources of ignition, so that is kept as one. Next, startup event. Okay, after this is an event, a startup event after plant shutdown, so that is again considered once in 4 years against the time at risk. So when we are saying one time in 4 years. You have to provide a time at risk against every year. So that is why it is one time in 4 years, which gives you a factorization of 0.25. Fine. So based on this, the total what you get is again sum of all product of all these, and that is 1 into 10 e raised to minus 7. Okay. Now, if you look at this mitigated, this is the same TMEL for this event also, which comes to multiple UO fatalities, which is UK fatalities, which is 2 or a single public fatality, and based on that you get 1 10 raised to minus 6. So as it is evident in this case also, there is no gap because this IEL which is calculated is lesser than the TMEL. Fine. That is why it says no gap, and then once it's no gap, then I'm saying the actions of the conclusion here is similar, that for the existing infrastructure which you have considered SIL 3, provide low temperature trips to safeguard the scenario. Okay. So with that done, let us now go to the big elephant, which is essentially the third scenario. So any concerns with these two scenarios, let me know now itself, so that we can go back and try to address or the relative comparative study. So we've discussed these two scenarios. First was this one, second one was this one, lesser than this. Now is the third one, where you need or where you foresee a need for additional safeguards or risk reduction or higher SIL required. Okay. So you guys are with me? Everything fine? Shall I proceed to the next case?
Sorry to interrupt you. It's already 3:01. So can we take a 10 minutes short break before starting the third case?
I think only 10-15 minutes is left for closing. You want to go for a break? Before that break, I think we'll have finished up.
Okay. Then
because I want to have this continuity of the system. No, they are comparing those two cases. Let the third case be also compared. Otherwise, there will be discontinued system, and then everything will be lost. Probably we will finish early, maybe half an hour early, but 10-15 minutes, I think we should be finished. So any concerns with these first two cases? Okay, if not, let's proceed to the third case. Okay, and this is very interesting. So may I please request you all to have your double attention here. Okay, so now this is a scenario where you have this FB for FB 101 stuck closed and no flow of hot air to the startup or burner heater. Okay, now this is similar to this scenario. In this scenario, it was stuck open. Okay, the same FB. Just so that you guys are able to do a relative study, I have kept the similar cases. The same FB which was on the flow line, there it was stuck open, here it is stuck closed. This is your PNID. And that is why I was saying it is good to do this now itself because it's a relative study. So this is the same FB 101. In the earlier case, we said it is stuck open. In this case, it is set stuck closed. In the second case, you are dealing with this valve, which is partially closed. And in this third case, this one is stuck closed. Okay. So what happens if this valve is stuck closed? Let's look at the description. Okay. So what does the description say? Okay. If this valve is stuck closed, correct, there will be inadequate air to fuel ratio in the startup heater to achieve complete combustion of hydrocarbons, resulting in uncombusted fuel gas and air mixture passed on to downstream, where it can combust. So basically what they are saying is, if there is if this valve is closed, basically their air to fuel ratio, that will be small because there is no air at all, and whatever is there is basically only fuel gas. So that means that combustion mixture is predominantly comprising of fuel gas instead of this combustion air. Okay, and that is the reason there is a good possibility that this fuel gas in much larger volumes than the earlier two cases will be passed on to the combustion reactor, leading to similar reactor damage and multiple fatalities or a single public fatality. And that is why this TML is same, I 10 raised to minus 6. However, now here is where we come to the part. Okay, so here what is happening is, if you look at this wall stuck closed, we are saying 0.2. Okay, 0.2 again because it is a control loop failure, so we are taking as 0.2. Now again, this is a startup event because the startup heater we are saying once in 4 years, which we will taking credit in the condition modifiers. Now looking at the safeguards, if you look at the safeguards here are typically different. Okay, if you don't have that, we are not taking the credit of the operator and other things. Okay, so here you see what we are saying is provide automated ESD valve. This was something which came from the recommendation. Okay, so here I'm saying provide automated ESD valves on each of the hot air lines, propane gas line and fuel gas lines to the burner. Provide permissive to open these ESD valves on fuel gas and propane line only when there is established flow in the hot air line. So this recommendation has come from the HAZOP, okay, and that was the reason why this recommendation came was because there is absolutely no safeguards in this scenario. Like if there is this valve is stuck closed, there is absolutely no combustion at all, or maybe there just at the initial phase itself there will be no lighting of the flame itself. So even your detectors or whatever is there, it would be as good as in a startup conditions or like a cold startup, because the flame has never been able to establish. Unless you have hot air or the combustion air, the flame would not start itself. So that detectors which are here in the PNID, the detectors which are here in this PNID are redundant, because since there is no air, combustion air for starting, the flame would have never lit up in the first place. In the first two scenarios, the flames would have been established, and after that only you would have been taken credit of these, because you would have seen the flames being established, and after that, because of no supply of fuel gas or this valve or blowout, flame blowout, this would have been like there would have been a flame, and then this would have shown no flame indication. However, in this case, if there is no combustion air, basically there is no means of initiating the combustion itself. So that is the reason this would never come into picture. This or this credit would never come into picture. So that is the reason I am not taking any of those credits. Okay, fine, fair enough. But during the HAZOP, this scenario was contemplated because this was a more grave and a catastrophic scenario, because there is more flow of combustion fuel gas without any air, and then air is surplus in the downstream system. So there you can get combustion air, and more fuel is passed on to the downstream heater. So it could have been a higher criticality scenario. So we deliberated that, and during the HAZOP, I had provided this recommendation. Now, what was the recommendation? It said provide automated ESD on each of the hot air lines, propane gas lines, and fuel gas line to the burner. Okay, and then it says that means first of all I need to provide 3 ESDs on each of these lines. Okay, because here you see there is no ESD, nothing, okay. So what I'm saying is this is a control valve, no on-off valves. Okay, although on-off valve would have sufficed, but since this is for a fuel gas system and a burner system, we have provided ESDs because all other systems were considered as still 3. So here I'm saying you provide an ESD here, you provide an ESD here, and an ESD here. Okay, that is what you have to do in the as a part of an HAZOP recommendations. Now, those in the same recommendation, I'm saying provide a permissive to open the ESD valve on the fuel gas line and the propane line only when there is established flow of hot air. That means you provide 3 ESDs and you provide a permissive, okay, to open this valve. That means the fuel gas or the propane gas, which is also acting as fuel, should only be opened if there is established flow in this line. That totally evades your scenario. That means none of these ESDs will be open unless this ESD opens first. So by doing that, by providing permissive, you are ensuring that there is not just fuel gas in your system, there is adequate air as well as fuel gas. Once there is adequate air, then you pass fuel gas, so you have that right stoichiometric mixture or combustion mixture available. Fine. So this was a recommendation that came up from the HAZOP. Okay. However, at the time of HAZOP, it was not contemplated that what level of integrity this safeguard should have. So that is why we have just considered it as 0.1 without any safeguard. As you look at the as the integrity chart, see, without any safeguards, we said it is just a safe. Without any safeguard, it would be 0.1. Okay, 0.1 or this, right? So that is how we have only considered this without any safeguards. So this is 0.1 based on a safeguard provided in the HAZOP without defining its integrity level. In this exercise, we may have to define the integrity level for this safeguard, but that was not established at the HAZOP stage. At the HAZOP stage, you just provide a recommendation that this is required for inherent safety of the system. And that is why I'm only taking credit of 0.1 for a safeguard provided. Next, here again, see, this is excess of CO fuel gas with this and air mixture resulting in 1000. So here again, I wasn't considering this, but without this safeguard, I will show you that this goes to SIL 4 level. So at that point, the operations team or the client team, they argued that even after doing these runs, they don't, or they contemplate that there is so much of excess gas from this line. This is the hot air line for combustion, whereas they say that there is so much of excess gas from this bypass line from the heater that they will never reach the composition of the LEL level. So based on their argument and rationale and their insistence to consider here, I've considered point 1. Again, if I had not considered this point 1, this would have gone to SIL 4 level, which was also a concern. So that is why we were at that point we did consider the client's recommendation to have this as a credible reduction. Okay. Now similarly, during startup, at least one operator is available. We have considered that as 1, and then time at rest once in a 4 years event. So we have considered 0.25. Now, if you see here, your total of these 3 products, your initiating event likelihood in this case is much higher than this. Higher because you see it is 10 raised to minus 4. Okay, 5 into 10 raised to minus 4, which is much higher than the TMEL. And it is higher by how much factor is this gap? So this is the gap. So it is higher by 2 into 10 raised to minus 3. Okay. So now that is the reason you see it is considerably high. So we need to do something here to ensure that the system is safe. Now, I have already provided 3 ESDs as a part of recommendation. Now, obviously, I don't want to add anything else as an infrastructure. But if I'm able to increase the integrity level of those 3 ESDs or those 3 system loops or safeguarding loops, I should be able to meet my requirements of SIL 3 as per client. Okay. So see here, the automated ESD safeguarding loop to be provided in the hot air, fuel gas and propane line of the startup heater requires to be SIL 3 rated. Okay, once I do the SIL 3 rated, further provide high integrity SIL 3 permissive to open the ESD walls on the fuel gas line only when there is established flow in the hot air lines. So now you must be asking me why only SIL 3 and not SIL 2. Okay, so just look at this value. It says 2 into 10 raised to minus 3. So once you get this value as a gap, so we are supposed to look at the table. Okay, see, you look at this table, or there is another. One second. There is another. Yeah. So okay, see, if a safety function is needed, the required integrity level can be determined as follows. That means you look for to calculate the PFD average of the probability of failure and demand. You look at the TMEL. In our case, it is 10 raised to minus 6, and based on the total scenario. So this is what gave us an answer of 2 into 10 raised to minus 3. That this function is calculated in this block. Okay. So this is what is the answer. Now this answer needs to be compared with the SIL table. So what was our answer? It is 2 into 10 raised to minus 3. So many a times people get confused looking at the PFD average because these values could seem confusing, greater than, minus than. To avoid that, simply find the risk reduction factor, which is 1 upon PFD average. And in our case, you have a value of 2 into 10 raised to 3. Okay. Based on 1 upon, if you look at 1 upon this gap, it is 2 into 10 raised to 3. Yeah, and that falls into this region. Okay, that is 2000. So 2000 would fall in this region between greater than 1000 and less than 10,000. So that is how we are reaching our SIL level of SIL 3. Correct? Any clarifications? And that is how we are providing this recommendation to consider everything as SIL 3 in this case. Okay, now the interesting part here is actually I initially, as I told you, I had not considered, or I was not insisting on having this as 0.1. I kept this as 1 based on the consistency consideration. In that case, it was crossing SIL 4. You see this? So it would have fallen in this range, SIL 4 and above, which essentially is not permissible by design or not a directive for the oil and gas setup at least. Secondly, just because of this, the client insisted that we guarantee that this scenario will not be possible because it never reaches that LEM level for propane, which is 21,000 ppm, and the resultant mixture based on their heat and mass balance was within 1000 ppm. So that is the reason we considered this 1, and that is how we get this SIL 3. Otherwise, it would have been SIL 4, and then they would have to redesign the whole system. So that is why they were also annoyed. and then we had to accept their rationale based that this is a credible safeguard. So yes, anything else? Any concern in what we just saw? Case 3. It is tricky, but maybe once you have the access to these PPTs and these files, we should be able to understand and contemplate or interpret what is the answer. Any concerns with this? Anything in the forum for case 3? What is the calculation between the IL and TMEL? Why? There is no calculation formula between IL and TMEL. They are two independent entities which we need to calculate and compare. See, this IL is based on the product of these things: conditional modifiers, independent protection layers, and the initiating cause event. Okay, so that is your initiating event likelihood. What you calculate, that is product of these three. And this TMEL is coming from the OSHA guidelines, which I showed you here. Where is the OSHA guidelines? Yeah, this is coming from the OSHA guidelines. So you are just comparing that product which you have determined there as IL to this TMEL, target mitigated event likelihood. And if it is less or if it is equal, there is no problem. If this is more, the IL is more, then you need a safeguard. Okay, as mentioned here. See, if you calculate these three, and if the IL is compared with the TML for associated severity level, if the IL exceeds the TML, then additional safeguard is required or risk reduction is required. So I showed you example where IL is same, IL is lesser, IL is greater, and where the safeguard is required, we have provided the safeguard, plus that integrity level was not adequate, so we changed the integrity level in the LOPA. Okay, fine. Okay, next we'll just see a couple of more slides. That is applicable criteria to designate an effective IPL. That is what I was saying. Wherever the definition for we can consider that as an IPL, even if it is a mitigative layer or a mitigative barrier. So what are the definitions? LOPA only takes risk reduction credit for any safeguard that meets the below IPL criteria. Okay, one is specificity. That means an IPL is designed solely to prevent or mitigate the consequence of one potential hazard event. For example, a runway reaction or a release of toxic material loss. So anything that is required or IPL is for specific initiating event, only then it is considered. It is to prevent or mitigate the consequence of a one potential hazardous event. So that is IPL is specific, or that IPL is specific to that event. Okay. Next is independence. An IPL is independent of all other protection layers. That means you could have a number of layers, your BPCS, your mechanical protection, but an IPL should be independent of other protection layers. That is, its performance is not affected by failure of another protection layer associated with identified potential hazards. So means based on any other layer or any other similar loop, suppose there are two sys loops. So it should be every independent sys loop should be independent without intermingling with the other loop. Only then you can call it as an IPL, okay? Or you can, if that criteria is not, but you just call it as a safeguarding loop. Next is effective. An IPL must on its own be capable of preventing the outcome of the concern when all other measures have completely failed. That means all other safeguards, whether a safeguarding loop or a control loop has failed, this IPL loop should be able to effectively overcome the safeguard or prevent the hazard. So it must have sufficient time, less than the process safety time, to respond to prevent the hazard event. Again, here it is important to have this IPL should have less sys time or less time than the process safety time for it to be effective. Okay. Next is dependability. An IPL can be counted to do what it is designed to do. Both random and systematic failure modes should be addressed within the IPL process design. Like it should be dependable. Like it should be able to whatever its function, its desired intent or function, it should be able to do it independently. Independently and dependably. Next is auditability. An IPL is designed to facilitate regular validation of protective functions, proof testing and maintenance of the safety systems. So auditability means whether that IPL is performing dependability again is part of the performability. Whether it is doing the protective functions, is there a proof it is providing? That there is called proof testing of each of the IPLs. They do it once in 6 months or once in a year. Many times they do it once in 2 years. And then maintenance of that system. Basically, it should be also maintainable. So they do maintenance, preventive maintenance once in 2 years, once in a year. So all these criteria, only if it fills this criteria, it is called as an independent protective layer, IPL. And the same thing for if the mitigation layers are able to meet these criteria as we discussed earlier, then you can designate it as an IPL. Okay, and then next is advantages of LOPA. Okay, LOPA is effective in evaluating the residual risk of a particular undesirable hazardous event, which we have seen. It is able to highlight if the current safeguards reduce the risk to a tolerable risk level. Yes, whatever considered in design, whether they are able to reduce the to a risk level, that is what LOPA says. And LOPA is timeless, resource consuming. It is less time and resource consuming than a QRA type study. As I said, QRA can stretch for 6 to 12 months. Next, it determines the risk gap between the residual risk of an undesirable event and a TML that is acceptable. Means the acceptable TML, as we have said, based on OSHA here, and what it is the residual risk, that you always get a gap which is very clear and evident. Next is LOPA is recognized as a technique for skill determination globally as per standard, which we are aware of. LOPA can be used to analyze safety. Similarly, we have done this exercise with respect to safety. Similarly, we can do it for environmental or asset and reputation to the risk application criteria. Based on the risk matrix, whatever is the benchmarking, the risk matrix. Yeah. So based on this risk matrix, whatever is the bench, like we have done it for people, okay, we're looking at the fatality, number of fatalities, injuries. But if your client wants it for environmental, whether it is a minor impact or a small impact or asset damage based on the value, 100 million, 1 million to 100 million, 1 million to 10 million, 10 to 100, or more than 100 million, based on that, or based on reputation. Reputation is also important because that can, like, you see the BP Mechando has a black spot on BP's performance in spite of all conservative safeguards it has in its design. So that's the reason the reputation could also be impacted, and that is why they are saying, so there can be a separate study done based on for the reputation also. Okay. So that is the advantages of LOPA. So then again, as everything has advantages and disadvantages also. So LOPA is not an hazard identification or risk assessment tool. It needs, so basically a hazard identification or a HAZOP or a HERA, you need to have that in place before you go a LOPA. You can see it needs to capitalize on the previous hazards and hazard studies. So it can capitalize on whatever are the findings from the hazard, HAZOP and HERA. But it is not an independent tool to evaluate the hazard, okay? LOPA is limited to evaluating a single hazard event scenario at a time. If the top event can lead to a number of hazardous events, and the risk reduction measures have to be determined for each hazardous event, multiple LOPAs. That's what I was saying, if you have multiple consequences leading to multiple events, they have to be addressed separately through a different, like a separate LOPA exercise. You cannot do a common mixture of all of those things, in which case you will get an absolutely wrong result. So it has to be dealt independently for independent initiating events. Okay. Then a LOPA study cannot be used to replace the good engineering practices. Again, these are important, right? Relevant good engineering practices are important because they determine the design of a system. LOPA is only to ascertain the safety of a system, right? Then LOPA is not suitable for assessing complex problems where the multiple shifts are protecting against different causes of the same hazardous event. That is for a burner management system where the hazardous event is deflagration within the firebox. So yeah, what they are saying is not suitable for accessing multiple complex processes where there are multiple shifts. Okay, there are multiple safety integrated systems and are protecting against different causes. Like there could be for one event, there could be multiple causes. As I told you the flare example, right? A spillover and localized vapor cloud explosion, and at the flare liquid carryover. So in such cases, it is not possible to use LOPA because there are different causes for the same hazardous event. Okay. In that case, like example of a burner management system, your hazardous, you need to use a fault tree analysis. They call it FTA. So that will give for each cause initiating event, for each consequence, what is the safeguard. So it will evaluate it, segregate and evaluate it separately. Next, it also has limitations where the SIF under analysis has sensors that protect against different hazardous events. Okay, but act on the same final element as LOPA does not consider common failure. So exactly, if it has multiple sensing events, but it is eventually acting on the same final element, like if it was acting on the same ESD or same pump tripping or same this, then it is not possible to take credit However, for our burner management system, we have taken credit because that burner management system was itself SIL3 rated. Okay. Next. Now, coming back to the first question which we asked you at the start of the forum, at what percentage of data we can capitalize on from the HERA or the HAZOP process? And the actual answer is almost 50 to 70% of the data can be leveraged. Where we can leverage that is at these different instances. In a HERA, you look at, in the HERA, you develop information for consequence. The same consequence can be considered an hazard event or a hazardous event where you define the initiating event. Okay. Then this consequence severity. This severity, as we looked at the severity 3, 4, 5, and 6, that itself gives you the severity level of a LOPA, whereby you get a TMEL out of this severity level. Next, what is the cause of during the HAZOP? The same cause can be considered as the initiating event. You just redefine that as initiating event and you attach all the enabling events to it, and that becomes an initiating event. So you are leveraging from HAZOP there itself. Then the cause frequency. So this cause frequency means we have determined the likelihood, right, in the cause. When we looked at the risk matrix, at the top we had A, B, C, D. That was the likelihood. So same that initial cause frequency is used here to define that as initiating cause likelihood. ICE, which is our initiating cause likelihood. That is the start of our event or LOPA analysis. Next is the existing safeguards which we have considered in HAZOP. We can take them as protection layer. That is what is the best example I showed you. The third case where we have considered all the safeguards in the HAZOP, but there I had only considered it as an individual safeguarding group, and that is why it was considered as 1 upon 10 or 10 raised to minus 1. However, I was able to use the same safeguard and increase its integrity level, after which we were able to consider it as a SIL3 safeguard. Next, recommended new safeguard, correct? So same, the required additional mitigation. So whatever safeguard which we had considered, we could use that as an additional mitigation. So I think, yes, with that, we are at the end of this presentation. So I hope you guys were able to follow. Sometimes I am pretty more eloquent, so I may be inclined to go faster. But I hope, like those 3 examples I took was deliberately from the same PNID, same system, same client, and just a relevant study to indicate how exactly for the same scenario, same loop, how the cases can be vastly different, whether you need a listen. So, is there anything else you guys want to use? Yeah, any concerns you guys, like anything you want me to repeat or something? No, not just OSHA guidelines. You follow, like, mostly the NORSOC project. Some follow NORSOC guidelines. The Scandinavian countries, and OSHA, basically UK guys, they follow UK, Europe, they OSHA guidelines. Then US has a different set of guidelines they follow, NFPA and other guidelines. So it all depends upon which client, which location, other things. Yeah, I think I don't see any more concerns or technical things here. But require more time. Is it okay if, yeah, you can mail these to all queries? I may not be able to respond to it immediately because I have some pre-commitments for the next couple of weeks. But definitely there should be a response. You can mail it to Shalini and then we can discuss. Yeah, that I agree, Mr. Jairaj, that even in a paid session, they are more focused on the money-mindedness part of it. And that is why they run through the sessions, or they don't want to reveal the trade secrets of this. So many a times the technical presentation is inadequate because they don't, in a paid session, they don't want to reveal the trade secrets. But obviously, like Yashpal sir's objective, and I'm glad to be part of that noble cause. We wanted this to be, reaching maximum recipients and with a noble objective at free of cost, so that people take a conscious decision whenever they approach any safety study in the future, or even retrospectively look back at their previous studies to address all these gaps very objectively. So I hope you guys will do it. And like I said, never succumb to pressure because you are susceptible or you are answerable to any shortcomings that can happen in the future. So, as designers, as process engineers, as safety consultants, you please take your stand, because you are the technical authority of your subject or domain, and you need to defend your design and your rationale to it, unless there is something which is like the other case, example 3, where the client insisted that they can demonstrate from the heat and mass balance that it doesn't go to the LVL and HEL range. Only after that I had to capitalize or accept that argument. So unless they are able to objectively resolve that with or demonstrate with results, you can stick your ground, because safety is something that is imperative, and it is a prerogative of the designers to look at it more objectively. So good luck with your future designs, and if you have any concerns, please direct the questions to Shalini, and after a couple of weeks we should be able to answer that. Fine, Shalini?
Yeah, sir. Sir, thank you so much. I would also like to thank you also, and as well as the participants also for their active involvement and the questions.